Warm welcome, everyone. Glad to be here with you. So, we'll continue the lecture on numbers. We did numbers one. This is the second part of the numbers of the three. So, part two of three of the numbers. So, in the part one, as you might remember, we talked about the classification of numbers. We looked at the importance of it from the aptitude perspective. Then we also looked at the divisibility rules, and then we looked at the questions built on the remainders, especially on some of the basic parts of the remainders on divisibility rule. So these were the two major aspects covered. Of course, there were all minor ones, so which were a part of these two major topics. And as I informed you in the previous lecture, we are starting off with the LCM, HCF, and already we'll also take some small concepts like highest power of a number in a factorial, how to find the unit digit. All right, this would comprise the second part of the lecture. The major component is the LCM, HCF, of course, so that because there are a lot of applications that would be built based on that particular concept. So we'll spend significant time on that, and then there are certain minor concepts which will focus. Coming to the third part of the lecture, so we will again focus on two major elements there, the factors and the remainders. Right, that's going to be the roadmap for today and the forthcoming lecture. Right, here we go. So there are two quick announcements before I start with the lecture. So one, you guys have any doubts while I'm doing this particular lecture, use the Telegram group. And you know the Telegram group, so which is in that Telegram group, post your doubts if there are any doubts, some of which I will take it up. So second, if you are not added on to the Telegram group, add to the Telegram group. So add to the Telegram group so that you will be able to post lectures on the Telegram group, and those queries gets addressed, right? And number two, so you have the EOM 7 Endeavor Online Mock CAT 7. That's window opening tomorrow and day after. So 2 days the window is open, and it's in the new pattern of CAT. You must have heard about the new pattern of CAT where each section is for about 40 minutes, and it's a 2-hour paper all in all with the same three kind of sections. It's a 2-hour paper, so you will get the first experience of it maybe if you take the test tomorrow or day after. Right, here we go. So let's get started with the numbers. Let me introduce to LCM and HCF without really taking things for granted. So here we go. So this is, so let me quickly take you about what we do on the LCM, HCF of what is that important to us. LCM and HCF can be found out for all positive real numbers, right? So as you may be aware, right, it is technically designed for all positive real numbers, right? It is designed for, right? It is designed for all positive real numbers. It is designed for all positive real numbers. LCM, HCF can be found for all positive real numbers, which implies there cannot be LCM for the negative numbers. That's right. So if I say, hey, what is the LCM of minus 6 comma 12? Let's say, it does not exist. What is the HCF of minus 6 comma 12? Doesn't make sense, right? LCM and HCF are designed for all positive real numbers. I introduced real numbers in the previous lecture, right? So therefore real numbers is what? It is both rational and irrational. We said that, okay, real numbers can be irrational, real numbers can be rational. Now under the rational, we also talked about the numbers which are integers, numbers which are non-integers, nothing but the fractions or decimals. Either we can write this as fractions or decimals, right? Yeah. So therefore, from the exam perspective, more often than not, we need to have a complete control over how to find the LCM of a positive. Now, so rational numbers, let me take it as a positive real numbers, right? Now positive, because I'm talking about positive real, so positive rational and positive irrational. Therefore, positive integers, positive fractions, and decimal. From the test perspective, these two are important to us: positive integers and positive fractions and decimal. How do I find the LCM and HCF of it? Let me spend some time there because that's very important, because some of your lectures of the future on arithmetic, for example, the lectures of time, speed, distance, time and work, we use this concept of LCM there, to resolve some of the issues of the time and work and time, speed, distance. So having a strong hold here is pretty essential. So let me first introduce you to that. I'll let a couple of methods that you would have done. Find the HCF and LCM of 12 and 15. We all know. Now let me first focus on LCM portion of it. LCM of 12 and 15. One is the long division method, no doubt. Or let you take 12 and 15. What is the long division method? You found out that which is the number which divides them. Okay, you may say that 3 is the number. 3 4 times, 3 5 times. Now you realize that, hey, can I take anything common between 4 and 5? Nothing. Therefore, the LCM is 3 into 4 into 5. This is the long division method, right? There's a long division method. So 3 into 4 into 5, which becomes the LCM, which is nothing but 60. Right? Therefore, you would say that LCM by the long division method is nothing but 60 for the given numbers. Good. What is the other approach? The other approach is you will look at the larger of the given two numbers, 12, 15. You look at the larger of the given two numbers, you keep taking the multiples of it. What is that? 15 one time, 15, 15 two times, 30, 15 four times, 45, 15 three times, 45, 15 four times, 60. These are the numbers which stick in your mind. You take the larger of the numbers and keep putting the numbers in your mind, and then you keep checking. Well, now does 12 divide this? Does 12 divide this 15? Answer no. Does 12 divides this 30? No. Does 12 divide this 45? No. Does 12 divide this 60? Yes. Therefore, 60 becomes the HCF. That's another way. Okay, what if there are three numbers? Same way. Three numbers, take the largest of the given numbers. Take the largest of the numbers and then keep all it now taking its multiple in your mind and keep checking whether the other two numbers divide it or not. All right, that's another method of this. Right, that's another method. Other one is what? Resolving into the prime. Right, you take the same numbers 12 and 15. You take this 12 and 15, you resolve it into prime. Hey, what is this 12? This 12 is nothing but 2 raised to power 2 into 3 raised to power 1. What is this 15? 15 is nothing but 3 raised to power 1 into 5 raised to power 1. Resolve it into primes, right? Resolve it into primes. We learned this art in the previous lecture. Resolve it into primes. Once you resolve it, look for the different primes that you have listed throughout. Look for the different primes you have listed. 2 is one of the primes you have listed. 3 is another prime that you have listed. 5 is another prime that you have listed. These are the three primes that you have listed here, right? 2, 3 and 5. These are the three primes. Look for the highest power of each of those primes. Look for the highest power. Okay, what is the highest power of 2? It comes from here, 2 power 2. Right? Highest power of 2 is 2 power 2. Sorry, just a second. Right? What is the highest power of 2? The highest power of 2 is 2 power 2. What is the highest power of 3? 1. Either you look here or you look here, doesn't matter, it is 1. Okay, what is the highest power of 5? That is also 1. Multiply them, you get the same LCM, which is 60. Three approaches. Basically, what I'm taking is three approaches. Either you follow the long division or you follow the solid, what we do in the mind. Basically, we take the number, we take the larger of the given, largest of the given numbers, take its multiple. From there, you can find out. That is the method 2. What is the method 3? Resolve them into primes. Resolve them into primes, and from there also you can find out, right? Three methods. All right, three methods. Right, let's go to the HCF of the same two numbers. HCF of the same two numbers. Again, you can do by the long division. It looks something like this. HCF of 12 and 15. You take the smaller number, you divide the larger number by this. Right, you will say that, okay, 12 1 time 12. Therefore, the remainder is 3. Okay, now once you have this remainder 3 here, well, this remainder, now you take this number, you take the divisor there, right? You put the 15 here, then you will say that 3 5 times is 15, therefore the remainder is 0. Okay, what was the last divisor for which you got the remainder 0? The last divisor was 3. This was first divisor, this is the last divisor. What is the last divisor? Last divisor is 3. The last divisor is called as the HCF. Therefore, you say that HCF of the given numbers is 3. Alright, therefore the HCF of 12, these are all school method, primary school method, what I'm talking. Right, HCF of the given numbers is 3, and just in case already you have some cumbersome numbers, method should be known. Alright, for 12 and 15 you don't know. 12 and 15 is an illustration. One look at it, you know that the HCF is 3, no big deal about it. But then what is the method? Just in case you get stuck, what was the method? That is one. Second one is resolving into primes again. 12 and 15, you resolve it into primes. Okay, what is 12? 12 is 2 power 2 into 3 power 1. What is 15? 3 power 1 into 5 power 1. Alright, that is nothing but your 15. So from here, what do you do here? You'd say that, all right, now from here, all right, now, so you take the common prime. First of all, you look for the common prime. Unlike LCM, where you looked at every prime. First, you look for the common prime between the two numbers. There is only one prime common. All right, that is 3. 3 is the common prime. Look for the least power. Look for the least power of 3. Common prime, and then look for the least power. 3 is a common prime between the two. What is the least power? It doesn't matter where you look. Anyway, it is 2 only, 1 only. Therefore, you are looking for 1. Alright, that gives me the LCM and HCF of the given numbers. Pretty simple one. There are two approaches to find the LCM, HCF. You have this and you have this. Of course, I will speak about further more approaches for HCF. There is one more approach that we follow. As I go along, I will speak about it. So this is about LCM, HCF. Alright, in case, alright, now so you have a trouble finding. These are the approaches you learned in the primary school. Alright, let's go further. Let's go further. Let's see this. Okay, here we have a question that's at the bottom. Second question. Let's try and answer that. Let's try and answer that. The numbers have been already resolved into prime. There are two numbers. This is the number 1. This is the first number. And this is the first number. And here we have the second number. There are two numbers. It's been already resolved into prime. 2 power something, 3 power something, 5 power something. It has been already resolved into prime. If I am finding the LCM, what I should do, list down all primes that you could, all distinct primes that you could see. List down all distinct primes that you could see. And then do what? Look for their highest power. Look for their highest power. What about 2? Well, now 2, you have a 3 and you have a 4. Look for the best of them. Best of them is 4, shortlisted. That's what I got to write it here. Okay, what about 3? Well, for 3, I have a 7 and 2. Look for the best of them. The best of them is 7. Therefore, I use 3 raised to power 7. What about 5? Similarly, the best is coming here, right? Now 3. All right, now therefore 3. So therefore, you say that hey, this is nothing but the LCM of the given numbers. All right, this would become this forms the LCM. What do we do? First, list all distinct primes and take their highest power. List the distinct primes and take their highest power. Okay, what about the HCF? What about the HCF of the same numbers? First, look for the common primes. Is 2 common? That's the first question you got to ask. Is 2 common? Yes. Already is 3 common? Is 3 common? Yes, 3 is common. Is 5 common? Yes, 5 is common. Already you are looking for the common ones. Once you look for the common, find the least power. Alright, least power of 3, least power of 2. There is a 3 here and there is a 4 here. Like the smaller of the 2. Therefore, that is 3. Smallest, alright, least power of the 3. Alright, now there you write it as 2 from the other side. Alright, now you write from the other side 2. What is the smallest power of 5? It is 1. Alright, therefore, alright, now it becomes the HCF of the same given set of two numbers. Right? Okay, you must be comfortable by now. You must be comfortable by now. So some of the property, also, alright, let's look at the fractions here. Let's look at the fractions. They were the integers there. Alright, that's the natural numbers. Here we have the fractions. So if I want to find the LCM of the fractions, what did we learn? LCM of the fractions. If I want to find the LCM of the fractions, A by B, C by D, and E by F, whatever it could be, how many sets of number, how many sets of fractions, doesn't matter. Nothing but LCM of the numerators. LCM of the numerators, that is A, C, and C, divided by HCF of the denominators. Alright, divided by HCF of the denominators. What is it? B, D, and F. Alright, this is what you would have learned. Hey, what about it is the HCF itself is the question. HCF of the same fractions. Fraction means there is a numerator and a denominator, right? HCF of the fractions, same way, A by B, C by D, E by F. So if I were to find the HCF of these fractions, find the HCF of the numerators, that is A, C, and E. HCF of the numerators, and then find the LCM of the denominators, that is B, D, and F. Let's take the simple example to illustrate this fact. Let's take this example. So I want to find the LCM of two fractions. What is that? 25 by 18 and 40 by 27, right? I'm finding the LCM of these two fractions. Find the LCM of the numerator. What is the LCM of the numerator? Which means I want to find the LCM of 25 and 40, right? So we already taught the methods there. LCM of 25 and 40 is 200. LCM of 25 and 40 is 200. Okay, then do what? Find the HCF of the denominators. Highest common factor of the denominators, which is 9, which becomes the LCM of the given fractions. I already taught you how to find the LCM and HCF. This forms the LCM of the given fractions. Okay, what if I want to find the HCF of the same given fractions? What if I have to find the HCF of the same given fractions, that is 25 by 18 and 40 by 27? So find the HCF of the numerator. What is the HCF of the numerator? HCF of 25 and 40, right? So okay, let me write one extra step if you want. So HCF of 25 and 40 over LCM of the denominators, that is 18 and 27. Well, okay, so what is the HCF of the numerators? HCF of the numerators is 5. Alright, that is 25 and 40. The HCF of the numerators is 5. What is the LCM of the denominators? Right, LCM of 18 and 27, which is nothing but 56. Alright, which is nothing but 58. Right, LCM of the denominators, which is 27 into 2, which is nothing but 50. Right, yeah, so that forms the HCF of the given fractions. That forms the HCF of the given fractions. All right, let's take a look at the one at the bottom here. Let's take another one at the bottom. another one at the bottom. So by now already you have got hang of this. Do it with me. All right, just do it with me. HCF and LCM of the given fractions. All right, so let me find the LCM. LCM of the fractions, 5 by 60, then 48 by 9, then 48 by 9. Okay, so LCM of the numerators, that's what you do here. LCM of what? 5 comma 48. The HCF of what? HCF of 60 comma 9. HCF of 60 comma 9. Fantastic. Let's do this. Therefore, what is the LCM there? 240. What is the LCM there? 240. Okay, what is the HCF of the given numbers? Which is nothing but 3. What is the HCF of the given numbers? 60 comma 9. The HCF of the given numbers is 3. All right, so therefore all right, that should become how much here? All right, that would become 80. That is what we get. Now if you do this, it is wrong. All right, 80 is wrong. You may wonder, hey, what is wrong? We followed the correct procedure. We followed all the procedure there. LCM of the numerators, HCF of the denominators. Why should it be wrong? Right? Yeah, it is wrong because you got to already, when you are finding the LCM and the HCF, the numbers should be in their simplified form. The numbers are not in the simplified form. Earlier, 25 by 18 is it in its simplified form. 40 by 27 was in its simplified form. Here, 5 by 60 is not in its simplified form. Hey, what is the simplified form of this? Already you would say that 5 one time and this is 5 12 time. Hey, what about the next one? Yeah, 9 and 18, 9 and 48, they were also not in its simplified form. Therefore, you would say that 3 times. All right, 3 times, and then you will say that okay, this is nothing but 316 times. Fair enough. So now look at that. What I was supposed to be finding. I was supposed to be finding LCM of 1 by 12, comma 16 by 3. Now these are the fractions in its reduced form. Remember, while you are finding the LCM and HCF of fraction, the fraction should be in its reduced form. Well, the fraction should be in its reduced form. Otherwise, we'll hit the wrong answers. Now what we should be doing? LCM of 1, comma 16. Right, and then we'll be finding HCF of 12, comma 3. All right, thereby your result becomes 16 divided by 3. All right, that is the appropriate result. 80 is not the answer. So 80 is not the answer. 16 by 3 is the answer. Point clear? So point is that while finding the LCM and the HCF, the result, or the fraction should be in its most simplified form. They should be in its reduced form. Right? Otherwise, we'll hit the different answer. Expected answer would be different from what would have got there. Similarly, while finding the HCF as well, by now you would have got the hang of this. All right, HCF you can find out the HCF of the same two fractions, HCF of 1 by 12 and 16 by 3. What is it? HCF of the numerators, which is 1, LCM of the denominators, which is 12. Alright, your result will become 1 by 12, LCM of the denominator. That becomes the HCF of the given fractions. Well, okay, let's go to the decimals. How do I find the LCM of the decimals? What if I have the decimals? Assume as if there is no decimal there. Assume it like my numbers to be 11, number to be 121, and number to be 1331. Assume like this. While you are doing the HCF, LCM, let me do the LCM of the given numbers. Already you are doing the LCM of the given numbers. While you are doing the LCM, assume as if there is no decimal points, as if there is no decimal point, take their integral part, and find the LCM there. You know, you will understand that LCM of these particular numbers is 1331. Because each of those numbers divided 11 divides 1331, 121 divides 1331. Why? It is 11 power 1, 11 power 2, 11 power 3. What's the LCM of 11 power 1, 11 power 2, 11 power 3? Because this is 11 cube. Well, this is 11 cube, this is 11 square, this is 11 power 1. So simple one, therefore it is nothing but 11 cube. That becomes the LCM there. So 1331, fine. Then what you do is look for the least of the decimal places. So how many digits are there after the decimal place here? 2 digits. Well, 2 digits after the decimal place. How many digits here? 3 digits. How many digits here? 4 digits. Take the least of them. What is the least of them? 2. Therefore count 2 places and put the decimal place. 13.31. That becomes the LCM. That becomes the LCM. Right? That becomes the LCM. Good. Now reverse of it. What if I'm finding the HCF of the same fractions? What if I'm finding the HCF of the same decimals? Same, all right, now assume as if there is no decimal. Assume as if there is no decimal. Find their HCF. Sure, HCF has become 11. HCF has become 11. Now what do you do? Take the reverse of it. Hey, what is the highest number of decimal places, number of digits after the decimal place? There are 4 digits after the decimal place. Maintain that. Maintain that. In the sense, put another 2 zeros, maintain 4 digits and put a decimal place. Put a decimal place here. All right, therefore the result becomes 0. Therefore the result would become 0. Just a second, friends. Okay, therefore the result in this case would be, yeah, all right, here the result would be 0.0011, right? So I will repeat quickly here. So while you are finding the LCM of the decimals, assume as if there is no decimal. So find, all right, now assume as if there is no decimal, like this: 11, 121, 1331. Assume as if there is no decimal. Find the value 1331 there. Find the value 1331 there, right? And then look for the decimal places, number of digits after the decimal place. In the first one, we have 2 digits after the decimal place. There are 3 digits after the decimal place. There are 4 digits after the decimal place. Take the least of them. Put the decimal place after those many places. It becomes 13.31, right? And similarly, while you are finding the HCF of the decimals, find the HCF assuming as if there are no decimal numbers. Find that, and then go for the highest number of digits after the decimal place. One of the, now, so it's 4 here. So therefore, create 4 digits. After the 4 digits, put the decimal place, which would result in 0.0011. Right, great. All of you have got the point here. Let me proceed from here. Let's proceed from here. Let's go to the next one. Well, that's about finding the LCM and HCF. Let's go to some of the simple properties out here. Let's go to properties. Let's go to properties. Just give me a second. I'll adjust this. Better. Fine. Let's go here. All right. So here we have, all right, now some of the properties, this important one. So because sometimes you get very simple question in some of the exams. Product of 2 numbers is nothing but their LCM, product of their HCF and LCM. True only for 2 numbers. Okay, now don't extend it to 3 numbers. Don't write it as number 1 into number 2 into number 3 is also nothing but their HCF and their LCM. Wrong. All right, it is not necessary. All right, this won't be necessary. Yeah, sometimes it is true. All right, let's not worry about it, but it is not necessary. All right, now it is definitely true for 2 numbers. It is definitely true for 2 numbers. For example, if my numbers are 20 and 30, let me take 2 numbers here, just to illustrate my point. Number product of 2 numbers is nothing but their HCF of what? Same 2 numbers, and their LCM. Right? Okay. Product, let's take simple numbers here, 20 and 30. 20 and 30. All right, now is nothing but what is their HCF? We know their HCF. One look at it, we know their HCF. What is it? 10. Here, what is their LCM? 60. All right, one look at the numbers. Assume that I provided the numbers 20 and 30. One look at it, you know their HCF is 10 and their LCM is 60. Right, therefore, all right, now, so we have this out here. Now, so while I write this 20, 30, listen to this clearly. Listen to this clearly. Somewhere, all right, now we falter at times at this point. HCF should be a multiple of the numbers. HCF should be a multiple of numbers as well as their HCF. Think about this 60. 60 is a multiple of 20. 60 is a multiple of 30. 60 is a multiple of 10. All right, now that's very, very important there. LCM is a multiple of the numbers as well as their HCF. Right, now LCM is a function. All right, LCM is a multiple of each one of them. Similarly, if you look at the HCF, all right, here is another one. HCF is a factor of all the 3 numbers. HCF becomes the factor of all 3 of them. Reverse. All right, now is the reverse. All right, 10 is a factor of 20. 10 is a factor of this number 20. 10 is a factor. 10 is a factor of 20. Put the other way around. 10 is the factor of 20. 10 is the factor of 30. 10 is a factor which implies 10 divides 20. 10 divides 30. Also 10 divides 60. 10 divides 60. Both links. All right, these 2 properties you should be clear. HCF is a factor of every given number. LCM is a multiple of every given number. Right? Now, multiple means it comes in its table. Right? Okay. So next one. So HCF of 2 numbers can also be written as the HCF of the differences, whatever we can do. I will come back to this point in a while. Keep it in mind. While I'm doing the applications, I'll come to this. Let's keep these properties in mind. Very important. Let's keep these properties. Now I'm taking up to the applications. All right, knowing this, let's take up to the application. Okay, here is a question for you. Product of 2 numbers is this and their HCF is this. Find their LCM. Fair. All right, now this was one of the exam questions. There was something like this. Exam question was like this. Great. Product of 2 numbers is 1, 2, 3, 0. So what do you write? You start by saying that number 1 into number 2 is 1, 3, 2, 0. Their HCF, all right, 1320, all right, 13. All right, first let's put it to perspective. All right, product of two numbers, N1 and N2 is nothing but HCF of the same two numbers and their LCM. Good. I anyway know the product. I might not know what is the number. I might not know what is the individually, what is the number, but do I know their product? Yes. Do I know their product? Yes. All right, I have it as 1320. 1320. Do I know their LCM? Yes. HCF? Yes. That is 6. Now what have been I am asked to find out? Their LCM. Fine. I can find their LCM. Great. All right. Now so we could find their LCM. Let's find the LCM of the numbers here. Let's find the LCM here. Therefore LCM is equal to, LCM is nothing but 1320 divided by 6. Simple. All right, divided by 6. I'm just transferring to the other side. So by 6. That results in what? All right, that would become 220. All right, 220. You get it as 220. That is the answer. All right, this answer option would be there in the exam. All right, the very first answer option, in fact, would be 220 because that would catch your eye. All right, then there would be a second answer option. All right, something like, okay, 120. There would be a third answer option. All right, which might be, all right, which might be 80 or whatever. Fourth answer option. All right, now fourth answer option, something. All right, now I will come to that. All right, fourth option is data inconsistent or none of these. All right, technically it should be data inconsistent. Now the answer for this question becomes data inconsistent. Why data inconsistent? What would we talk about that? All right, we said that okay, the LCM has to be of a LCM has to be a multiple of HCF. The LCM should be a multiple of HCF or HCF should be a factor. Now look at this. What did you get LCM here? 220. You got the LCM as 220. Is 220 a multiple of 6? No. Or is 6 a factor of 220? No. All right, now therefore what do you say? The data is inconsistent here. All right, mathematically we can get some number. Math said that take LCM as 220, but we know the property of LCM saying that okay, the HCF should divide the LCM or HCF should be a factor of LCM or LCM should be a multiple of HCF. We know that particular point. So therefore the property fails. Remember, it is not just about the math. All right, now this is a simple math. Product of two numbers is equal to product of another set of two numbers. That is fine. All right, this technically says what? Product of two numbers is nothing but the product of set of another two numbers. That's simply a math. That will not talk about the property. You need to understand that okay, LCM should be a multiple of a HCF or HCF has to be a factor of LCM. HCF should be a factor of the given numbers. All right, all that part we need to ascertain. We need to ascertain there. Okay, let's go to the next question. You might have got that point. Just to illustrate that point, here is another example. HCF of two numbers is 8. HCF of two numbers is 8. Which of the following can be their LCM? Can be. All right, following can be. Possibility. We are only talking about the possibility because already there is not too much of information. Or it is a very loose thread of information. HCF is 8. Which of the following can be their LCM? What do we know? We know that the LCM has to be a multiple of this 8. LCM has to be a multiple of this 8. All right, therefore 60 cannot be the answer because 60 is not a multiple of 8. 100 cannot be the answer. 120 is a multiple of 8. Therefore that is the answer. 140 is not a multiple of 8. Therefore that can't be the answer. Therefore can be. The word is can be. Can be is what? 120. Guys, so far it is good. Any doubts here? So far is it good? So far is it good? Going good? So far going good? Great. All right. All right. Here we go. Let's go with some of the application questions. All right. Let's go with some of the application questions. One of the exam questions out here. The HCF and LCM of two numbers is 21 and this. If one of the numbers lies between this and this, find the other number. Okay, I'll give a minute's time. I'll give a minute's time. Now that you understood the concept, right, for a minute. I guess everybody is sitting with a pen and a paper, pen and a book. It's important, right? It's a mental gym, guys. It's a mental gym. Don't sit and watch. Always sit with a pen and a book. And push your pencils a little bit always. You got to exercise your mind. Okay, time. Let's do this. HCF and LCM of two numbers is given. he's asking that if one of the numbers lie between, which means there are two numbers, all right, product of two numbers. If one of the numbers lie between this, one of the numbers lies between these two, then find what is the other number. All right, what can be the other number? Let's find out. Well, it is saying that, okay, sum of product of two numbers, n1 into n2, is also nothing but their HCF and their LCM. And their LCM. Now look, what did we understand? We understand that your first number should be a multiple of HCF. All right, therefore your first number, what is the HCF? You have 21. Therefore your first number should be of the form 21x. Your first number must be divisible by 21. All right, 21x. What about your second number? Second number also must be divisible by 21 because the HCF is the factor of numbers, both the numbers as well as the LCM. Good. Therefore the second number should be of the form 21y. Second number should be of the form 21y. Fair enough. So after this, all with the 21y. Now take a look at this. Therefore, if the 21 is the LCM 21. So also, all right, now you can also understand that x and y, here x and y, friends, x and y would be co-primes. X and y would be co-primes. Hey, why x and y are co-primes? Because if the 21 is the HCF, if you say that n1 and n2, 21 is the HCF of the numbers, then there can't be anything common between that x and y. If you say that, oh, between x and y, 2 is common, then the HCF should change from 21 to 21 into 2, which should become 42. All right, therefore, once you understand that HCF is the highest common factor, after that there will be nothing which is left. After that, all right, the only common thing between x and y would be 1. All right, x can be 4, y can be 9, as we said in the last class. X can be 4 and y can be 9 because they need not be prime. They should become co-primes. X and y should become co-primes. That is something that you have to keep it in mind. Is it really useful in this question? That's a different issue. But that much you should know. All right, that much you should know. Fair enough. Let's come back and write it. Therefore, n1 can be written as 21x. n2 can be written as 21y. HCF of the numbers given 21. LCM of the numbers given 4641. LCM of the numbers given 4641. Fair enough. Let's do the simplification. A 21 gets cut off with this 21. So now divide this solid 4641 by another 21. Another 21. So therefore it would become 2 times, and 1 time. Therefore you are trying to say that x into y. This 21 I am cutting off with this, which has become 221. Right? Therefore x into y has become 221. Fair enough. Now x and y should be co-primes. What is this 221? Try and factor them a little bit. You understand that x and y are nothing but 13 and 17. One of them has to be 13, one of them has to be 17. Hey, why did you write x as 13? I didn't write, I just wrote somewhere there 13 and 17, smaller number I wrote there, larger number I wrote there. Now let me go back to number 1, because he says that one of the numbers lies between 200 and 300. Fair enough. Let us say that n1 is the number which lies between 200 and 300. Therefore, this is nothing but 21 into x. Solid. Now, is this number n1 lying between 200 and 300? Is this solid? Now, if I multiply by x, let me take two cases. X can be either 13. X can be either 13 or x can be 17. One of the two values, because the value is 21x. X and y are not the values, friends. 21x and 21y are the values. So first let me find out that which number lies between 200 and 300, which is that number. So let me take two cases. There is a first case and the second case. Let me take the first case. If it does not work, then I will take the second case. 21 into 13. 21 into 13. I will take 21 into 13 there. Yeah. Therefore, now that is becoming 273. That is becoming 273. A 273 lies between 200 and 300. Perfect. Therefore, this is the number author is talking about. What about the other number? Therefore, I will take it with 17. That's my n2. N2 is therefore nothing but 21 into 17. 71 into 17. Now that will become 357. Which would become 357, which is your answer. Because the author is asking that find the other number. Which is the other number? I am telling you that one number lies between this. He is not saying which is that number. If one number lies between this, hey, what is the other number? This is how the questions come in the exam. Some simple questions come in the exam in this fashion. Therefore, you would say that the other number is nothing but 357. All right, there we go. We'll go to the next one. I have a pretty simple application. I guess all of you followed this. If you followed this, there was an involvement of co-primes as well there. Fine, let's go here. I said that, okay, we'll come back there and I will tell you a little bit about the HCF. Now look at this. Find the greatest number that will divide, now these three numbers. Greatest number that divides all these three numbers. That divides all these three numbers. Okay, in the sense, nothing but the HCF. What is the greatest number which divides them? HCF. If you say that what is the smallest number which divides them? 1. 1 divides. If I say that what is the smallest number? If I change this word to smallest, what is the smallest number which divides all these numbers? 1. 1 is the smallest factor. Basically, smallest factor is 1. Am I asking about this? No, I'm asking about the greatest one. What do you mean by greatest one? Greatest number is nothing but the HCF. Call it HCF of the given numbers. That's what we are saying. Fine. One is the long division. The other method that we talked about was, okay, resolving them into primes. So what is the other method? Take the difference, friends. I'm teaching you the method here. Take the difference. Simply take the difference between these two numbers, 144. Put the numbers in some order. Put the numbers in some order if it is not given. And take the difference if they are little neck to neck. If they are little closer, take the differences. Take the difference. Third method I'm teaching here. If there are lot number numbers, I'll take the difference. I took what difference between 144 and 168. The difference is 24. The difference is 24. Great. Take the difference between these two numbers, or take the difference between these two numbers. The difference becomes 72. Okay, take again the difference between these two numbers if you want, or check all it now. Already you have one of the smaller numbers here at this stage, 24. All you have one of the smaller numbers here. Now what you do is, all when you have this 24, take this number and check whether this 24 divides this, 24 divides this, and 24 divides this. This approach you can take provided your number crunching skills are fairly good. Your number crunching skills are fairly good. Okay, does 24 divide 144? Yes. If just it divides 144, anyway you got the difference of 24 because of the difference between these two numbers. It is dividing it. 24 is dividing it. Therefore 24 is the HCF. What if it is not 24? Take the smaller number, reduce it like this. What if it is not the 24? Then it becomes the factor of 24. Yeah, what do you mean by factor of 24? It can be 12. It can be 6, it can be 4, it can be 3, it can be 2, it can be 1. Go in the descending order. If 24 is not working, assume 24 did not work. Then to look for 12. 12 did not work. Look for 6. 6 did not work. Look for 4. Likewise. Likewise, you can go backward. Why? Because you are finding the highest one. Worst case scenario, it becomes 1. Worst case scenario becomes 1 because 1 is the factor for every single number. That's a worst case scenario. Now don't get confused. Let me illustrate this method as we go along. So whenever the HCF comes, I will illustrate this method because this method technically works pretty faster. It works very faster. As I go along, I will illustrate this. Now this question was just nothing but find the HCF. This question I have taken just to illustrate what are the other ways and means to find the HCF. Right now, here we go. There is a rectangular floor. The person has a rectangular floor. There is a rectangular floor of dimension 54 by 24, something like this, right? 54 by 24. If this is 54 feet, this is 24 feet. Okay, to be covered by using the square tiles, not any rectangular tiles. The tiles has to be square tiles of the same size, which means you are going to a ceramic shop or you are going to a shop and you want to order tiles. Tiles are of the same size. All right, tiles are of the same size and they are square in nature. Find the minimum number of tiles required, which means when you go to the shop, already you looked at a design, you liked that design. There are the tiles of dimension 1 by 1, already 1 by 1. There are the tiles of the dimension, same thing. All right, now the same pattern, you have the tiles of dimension 2 by 2. You also have the tiles of dimension 3 by 3, like this. All right, you have some tiles. You have some tiles. But the point here is find the minimum. All right, find the minimum number of tiles required to cover the floor. You want to find the minimum tiles to cover this floor. You want the maximum tiles to cover the floor. Now look at the opposite of this. Hey, what if I wanted the maximum number of tiles to cover the floor? Go by the size 1 by 1. Assuming that the sides are square size is a natural number, then go with the 1 by 1. Take small tiles of 1 feet by 1 feet and cover this land, cover this particular floor. That's a minimum. That's when you get the maximum number of orders, maximum tiles you have to purchase because you went with the smallest possible size. Yeah, I want the minimum tiles, but the question is the minimum number of tiles. If I want the minimum number of tiles, go for the big size. Go for the big size of the tile. No, let it be as big as possible, big and big. Same number, let it be as big size as possible. So as big means what? HCF. Therefore what you are trying to say, this question is nothing but you are supposed to be finding the HCF of 24 and 54. You are supposed to be finding the HCF of 24 and 54. Now listen to me. Okay, some things would have come into your mind, no doubt, but I'm just illustrating on my method. What is the difference between them? 30. Good. What is the difference between them? 30. Now at this stage of 30, what you can also do is take the smaller number and write with this 30. 24 and 30. Don't write the larger number. Take the smaller number. Life is simple. You take the difference between them. What is the difference here, friends? 6. All right. What is the difference between 24 and 36? You first took the difference between them. It became 30. Right? And then now you are saying that, hey, I don't want to deal with this 30 because 30 has been larger than this 24. 30 is larger than 24. HCF cannot be larger than the given numbers. Right? So therefore what you took one of the numbers. You put that number to perspective here, 24. You got the difference. Again, take the difference. It has become 6. Now either say, now at this stage 6. Now what's the either 6 is the answer or the factors of 6. What are the factors of 6? 3, 2, 1. Put them in the reverse order. Now check with this 6. Does 6 divide both the given numbers? Does 6 divide 24? Yes. Does 6 divide 54? Yes. Therefore, the tile size is 6 by 6. That is the size of the tile. That is the largest tile that you should use to cover this particular platform, cover this particular floor area. 6 by 6. Hey, what if 6 was not dividing these two numbers? Fine. Then you have to go for the, or you have to go for the better factor. What is the better factor after 6, 3? Hey, what is the, what is the lower factor than that 2? What is the least of the factors? 1. Least of the factors will get it, provided, or none of the numbers are dividing it. Always go for the better between the two. That's how you find the HCF. See, technically what I'm advocating, these things can happen in your mind. You take the difference, that becomes 30. You just take the difference between that, it becomes 6. When the numbers become larger at some stage, 2-digit numbers are fine. When the numbers become 3-digit numbers, etc., it becomes a lot easier to navigate with this difference method. That's a point I'm trying to make. All right, good. Okay, you have got the perspective on this. You have got the perspective on this. Let's go to the next one. Let's go to the next one out here. Okay, you tell me the answer, friends. Take a minute and you tell me the answer. Get me the answer to this question. Okay, got it? Great. All right. See, if you say that, okay, you can pack 1 kg also per bag. So what he's saying, all right, now this guy has n number of bags. He has good number of bags there. All right, this guy has n number of bags. He has some bags with him. They are big bags, big bags. The bags are big enough, let's say. He has n number of bags. You can pack 1 kg also. You can pack 1 kg. Already has 3 varieties of rice. You can pack 1 kg. If you pack 1 kg, 102 bags are required for this. 136 bags are required. 272 bags are required. So all in all, 610 bags are required. Right now, 610 bags are required. Right? 2, 3, 4, 500, 510 bags are required. If you add up these numbers, add up these numbers, 102 bags here, 136 bags here, 272 bags here. Right? So if you add up these particular numbers, it's becoming 510. Right, 510 bags. 510 bags are required when you put one at a time. That is maximum. Well, if you say that, okay, integral value you want to pack the rice with integer value. You don't want to pack quarter kg, half kg. You want to pack minimum 1 kg integer value. Then you understand that you at least need 510 bags. That's not the question here. He is saying that, man, tell me the least number of bags, minimum. I want to pack minimum number of bags. If it is minimum number of bags, then don't pack 1 kg. In fact, alright, pack n kgs per bag. Pack n kgs per bag. But that n should be common. That's what author is saying. Look, each bag should have the same capacity. I don't want various capacity. Each bag should have the same capacity and it should have the same variety. If I call this as the first variety, if this is the second variety, this is the third variety, don't mix up. Don't mix up. Either this bag should be made up of first variety or second variety or third variety, and the quantity should remain same. Therefore, what do you find? HCF. If that is the condition, if the bags has to be minimized, you got to pack maximum rice per bag. If you were to pack maximum rice per bag, that number is called as the HCF. Maximum means HCF of the given numbers. That is HCF of 102, 136 and 272. You are packing the HCF of these particular numbers. Great. All right, now let's go. All right, now that's what you're packing. Fair enough. Let's go to the difference of these numbers, which is 34. All right, difference of these two particular numbers is 34. Great. So if I take a difference here, all right, it may become larger than 34. No worries. Take this 34. Take one difference. Take this 34. Check whether the 34 is dividing this particular number. Does 34 divides this particular number? Yes, it divides. Does 34 divide this number? Yes, it divides. Check that the 34 divide this particular number. Yes, it divides. 34 the numbers. Take one difference, you will kind of hit that particular block. What if it is not 34? Take the factor of 34. Take the factor of 34, no worries. All right, take the factor. Hey, can I take the difference here also? No problem, guys. You can take the difference there also. All right, you can take the difference of 2 and then you can take the difference. But one difference also will work. Hey, what if 34 was not working? I don't write 17. I don't write 17. If 34 was not working, I don't write 17 there. Likewise, okay, 34 is working. Therefore, how many bags are required? If it is 34, then I need 3 bags here. If it is 34, I need 3 bags here. 34 into 3. 34 into 3 is 102, right? Yeah. So 34 into 4 is 136. 34 into 8. 34 into 8 is 272 because this number is double. All right, 272 is double of 136. All right, therefore 8 bags are required. Totally, how many bags are required? 3 bags for the first variety, 4 bags for the second variety, 8 bags for the third variety. Totally, I just need about 15 bags. If I pack only 1 kg per bag, I wanted 510. But if I pack 34 kgs per bag, I'll take each bag and I will take 34 kgs. I'll pack 34 kgs per bag of one particular variety in each. This is variety 1, variety 2, and variety 1, variety 1, and variety 1. 3 bags are enough for variety 1. Likewise, 4 bags are required for variety 2, right? 4 bags are required for variety 2. Second variety, we just need about 4 bags here, right? So each bag has again 34 kgs, right? Now, so that's how, so you understand that 15 bags are good enough here. We can't make lesser than 15. So this is how the application, some of the applications are built on the HCF. All right, some applications could be built on HCF. You need to be mindful based on the question. You need to be a little mindful based on the question. Okay, so I'm showing you a prototype of one of the questions. When I see the factors, when we learn the factors, we will see the mega avatar of this particular question. When we study the factors, that's in the next lecture. When we study factors, we look at the mega avatar of this. So let's take a mini prototype because the nature of this question is nothing but the function of HCF LCM. Nature is nothing but the HCF. Let's take a look at this question. I'll give a minute for you to think, friends. Minute for you to think. Please think about this. Think about this question. Think about this question. Yeah, good going. All right, let's see this. Sum of two natural numbers is 96. Sum of two natural numbers is 96. Let me call it as n1, n2. It's a pair. All right, there is nothing like n1, n2 here. For illustration purpose, I'm writing it. We can't interchange the values of n1, n2 there. It doesn't make sense. I'll come to that. I'll come to that later. Sum of two natural numbers is 96. 96. Their HCF is 4. Their HCF is 4 means what? N1 can be written as N1 can be written as already N1 can be written as the HCF is 4 implies what? N1 can be written as 4x. N2 can be written as 4y. I can write it as 4y. That's a meaning of saying that. Alright, now that's a meaning of saying that HCF 4 is the HCF. So let me write it here. This is 4x. This is 4y. Where x and y are co-primes. Where x and y are co-primes. I'm not saying 4x and 4y are co-primes because 4 is already common there. You take that common out, x and y becomes co-primes. That's important, which is 96. Good. So therefore, you realize that x plus y, or that x plus y is equal to 24. Yeah, what is that you are trying to say? X and y should be co-primes. That's what you said here. X and y should be co-primes to each other. Although n1 and n2 are 4x and 4y, in which x and y are co-primes. Why? HCF is 4. If you say that hey, there is something else common between them, it will not make sense, right? Okay, so therefore number of pairs author is asking, what if I write 1 here? If I write 1 here, I can write 23 here. Is the HCF of 1 and 23 is 1? Yes. All right, therefore these two are co-prime pairs. Okay, what if I write 2 and 22? Disqualified. All right, because the HCF becomes 2, because they are not co-primes. We already said that n1 and n2 should be co-primes. If I write 222, they are not co-primes because HCF becomes 2. HCF is 2 there, right? Okay, what if I write 3 and 21? 3 and 21, that's also disqualified. Disqualified. What if I write 4 and 20? Disqualified. Technically, you say that, okay, man, all right now, so even numbers are anyway disqualified because sum of two even numbers become 24, that disqualified. In your mind window, what are the numbers that you are checking? You check only for odds. You check only for odds. In a sense, you check for 1, 3, 5, 7, 9, 11. That's all. These are all the only testing cases. You may say, why these are the testing case? What's the problem writing 13, 15? All right, let me come to that. I'm taking a break even here. All right, I'm saying that at 11 we can stop. Let's see, all right, now why I'm stopping it there. If it is 1, this is 23. All right, 3, all right, now write down the numbers there. All right, this is 21, 19, because the sum should become 24. I'm writing the corresponding pairs, corresponding values, right? 17, then we have 15, and we have 13. See, when you write 13, you will be writing 1 here. That pair is already there. It's not an ordered pair, it's just a pair. All right, why? Because when I ask a HCF of, say, I'm just giving an example, HCF of, HCF of 4, 6 is 2, is nothing but saying HCF of 6, 4 is 2. Why you are changing the order? He just said that pair of numbers, sum of two natural numbers. That's it. He didn't say that 4 first or 6 first or 6 first or 2, 4 first. Didn't mean all right. Therefore, the order does not matter. Order does not matter. This n1 and n2 is solving mathematical perspective. It is not to do the order. You have to express that thought, right? Therefore, you wrote n1 and n2. If you write n and n, you will get confused. Then it will look like 2n is equal to, all right, now, so that's how it looks. Therefore, you wrote n1 and n2 for, all right, for mathematical purpose you wrote. Therefore, you will take a break even at this. You will say that, hey, okay, I don't want to repeat the numbers. I will stop here, stop my pattern here, find out how many of them are co-primes. 1, 23 is fine. This is not fine because 3 is the HCF. This is fine. This is fine. This is not fine because 3 is the HCF, and this is fine. So therefore, how many pairs I got? 4 pairs. All right, that's what you asked. How many such pairs are there? Your answer is there are 4 pairs. I'm not saying 1 and 23 are numbers, my friends. All right, your numbers are 1 time of 4 here, 1 time of 4, and 1 time of 21. What do you mean by 1 time of 4? I'm just illustrating this point. 1 time of 4 is 4. Okay, what is 1 time of 23? All right, 1 time of 23 is 92. I'm trying to say that 4 and 92 are the first pair of values. All right, whose HCF is 4 and whose whose sum becomes 96. Okay, likewise, now I found out 4 pairs out here, 4 pairs out here. The point is, hey, what if I change this, make this number big? I call it as 960. All right, then I need a method that I will discuss in the next lecture. That's the point I was trying to make. 96 is fine. If I make it 960, all right, or then you will say that, okay, there is a little problem here. So I cannot keep writing like this, all odd numbers that way. There should be another approach to this. I will come to that approach, but this fundamental approach should be known. Number is simple. Will this method work? Of course it works. No issues. No issues. Some simple question, simple number, it works. The number becomes big. That is when I need an alternate approach. I'll come to that because a little bit of basic is required on that. Some factor study has to happen. Based on that, we'll be able to capitalize on it. All right, yeah, let's go further. Let's go further. I think everybody's clear on this. Everybody's clear on this. Okay, just an extension of that. Extension of that. Try it for 30 seconds. Try it, take 30 seconds. Get to understand how do you start. Write that piece of information on your paper. Get a start. Good. All right, do it with me. The product of two natural numbers is 120. All right, that is n1. Let us write it as n1 into n2. Of course, n1 and n2, there is no order to it. For expression of thought, product of two numbers is 120. Their HCF is 2. All right, it's the given that their HCF is 2. Fine, if the HCF is 2, the first number should be written as 2x. The second number should be written as 2y, which should be equal to 120, in which x and y are co-primes, right? Again, we know that x and y should be what? All right, they should be co-prime pairs. All right, x and y should be co-primes. Because 2 is the HCF. Now there can't be anything common between them, right? Therefore, it should be co-primes to each other. So already you are saying that that's 120. So and hence you are saying that x into y is equal to 30. Just simplify this, simplify that equation. And wherein x and y are co-primes, write it as a product of two numbers. 1 into 30 is 30, right? 2 into 15 is 30. 3 into 10 is 30. Right, 3 into 10 is 30. Is there any other way that you can express? No, these are the 3 ways that you can express. Right, 3 ways that you can express out this particular number here. Right, 1 into 30. Right, 1 into 30. Then you are writing it as 2 into 15. You are writing it as 3 into 10. And then you write it as 5 into 6. Very good. Right, 5 into 6 is another way. Right, okay. Now let's find that, okay, are they co-primes to each other in the sense you are checking, is 1 and 30 co-primes? Yes. Or 2 and 15 co-primes? Yes. Or 3 and 10 co-primes? Yes. Or 5 and 6 co-primes? Yes. So which means this time all 4 pairs have turned out. Therefore, your answer is going to be 4. Well, all possible pairs are going to be 4. 4 pairs turned out and all 4 seems to be perfect. All 4 seems to be fine. Okay, that's about this question. So that's about it. So a little bit of application of LCM HCF. Application of LCM HCF. Okay, let's go to the next type. Let's go to the next type on LCM HCF. There are 3 models. All right, there are 3 type of other problems that does come in the LCM HCF. Let me illustrate them. 3 models in LCM and 2 models in HCF. Together, we have to quickly understand these 5 models. Let's understand them. It may take about another 20 minutes by the time we understand, but it's very important to understand this. Okay, because questions, so many times in most of the exams, you directly get the questions based on this. Let's take a look. Find the smallest 3-digit number which when divided by 6 and 9 leaves the same remainder 2 in each case. Okay, what is the first model? Constant remainder. So what is that constant remainder? Same remainder. Same remainder. That's a first model. First model is a constant remainder. Let me first do this question and then give the general form to you. General form to you. Hey, what does it mean? There is a number. First, let us find it. Let's not worry about a 3-digit number. Let's not worry about a 3-digit number. Let's just worry about, let me get one number like that. Why should I worry about so many numbers? Let me get one number. He said that, okay, look man, your number, well, your number can be written as 6 times of a multiple plus 2. Division algorithm. Why? Because when it is divided by 6, the remainder is 2. That's a division algorithm. That's how the number should be. Oh, let me write the series. Put n is equal to 1, you get 8. Put n is equal to 2. Put n is equal to 1, you get 8. Put n is equal to 2. Put n is equal to 2 there. 6 into 2 here. I'm putting the values here. Put n is equal to 2 there. You get 14. Then you get 20. Then you get 26. Then you get 30, then you get 30, then you get 32, and so on, so on. It's an infinite series. There is no end to this. It's an infinite series. Good. The same n can also be written as, 9 times of m plus 2. What is this 9 times of m? 9 here. It's when it is divided by 9, the remainder is 2 again. So therefore, it can also be written as 9 times of m plus 2. Great. How do I express this particular thought? Therefore, let put m is equal to 1, you get 11. Then you write it as 20, then you write it as 29, then you write it as 38, now so on. This is also an infinite series. Now look at this. What is the smallest such number? Therefore 20. What is the smallest such number? Therefore 20. If you say that, hey, 20 when divided by, assuming that, okay, quotient cannot be 0, m and n cannot be 0, just assume like that for understanding study purpose. You assume like that. Okay, 20 when divided by 6, the remainder is 2. 20 when divided by 9, the remainder is 2. Therefore 20 is one of such numbers. 20 is one of those particular numbers. Hey, is 20 the only number? No, there may be many other numbers. Hey, okay, think about this. Okay, you will get it as 36 here. What is the next number here? 38. Continue the first series, 38. Therefore now you are saying that, hey, I got another number. 38 is there here as well as here. I got 38, which is there in both the cases. Absolutely. Now, how do I define this particular series? Therefore, now listen to me. Listen to me. If there is a number, this is a series of numbers. There's a given question like this. There is a number. When divided by D1, leaves R as the remainder. When divided by D2, leaves R as the remainder. Constant remainder I'm talking about. R is constant. When divided by D3, still leaves R as the remainder. It can be two numbers, or it can be more than two divisors. It can be one divisor, or it can be two divisors, or more than two divisors. Leaves R as the remainder. Then the family of such numbers. It's not one number, friends. It's a family. It's not function. Family of such numbers. It's a series of numbers, or a series of such numbers. Right now, series of the such numbers is given by, and it is a function of LCM. It's a function of LCM. It's given by LCM of the divisors, that is D1, D2, D3. I'm not saying product. LCM of the divisors, k times LCM of the divisors, some k times, plus the constant remainder, right? You've got to remember this. Right? You've got to remember this. If I apply this in this question, my family of numbers in this question is nothing but LCM of my divisors. What are my divisors? 6 and 9. I have to take the LCM of 6 and 9, k times, plus what is my constant remainder here? 2. I would have added this. This is how I would have get the general form of this. So from here you will say that, hey, my family of numbers is nothing but LCM of 9 and 6, which is 18, 18k plus 2. 18k plus 2, right? Put k is equal to 1, or put k is equal to 1, you get one of the numbers. Put k is equal to 1, you get one of the numbers, which becomes 20. If put k is equal to 2, you get another number, or you get another number, which becomes 38. Likewise, he's saying that, hey, why don't you find the smallest 3-digit number? Fine. For a suitable value of k, I will get the smallest such digit number. All right, now for what value of k you will get it? Because you wanted a 3-digit number. You wanted a smallest 3-digit number. Therefore, number is equal to 18 into 5, all right, 90. Therefore, 18 into 6 you will do. Therefore, suitable value of k is what you are going to put it here. 18 into 6 plus 2, right, which will become 110. Right, which would become 110. 110 is the smallest such number. When divided by 6, leaves 2 as the remainder. When divided by 9, it leaves 2 as the remainder. Okay, all of you, I think you got the first model. My focus attention should be on this. Attention should be on this. When all attention should be on this particular area, writing this particular area. Or if there is a number, if author says that there is a number, when divided by a particular divisor, leaves R as the remainder. Another divisor leaves R as the remainder. Every time the remainder is R. Every time the remainder is R. This is the general form. This is the general form, right? This is the general form. Okay, now that you understood, I explained it here. Now that you understood, let me give the general form for the other two models as well quickly. Let me give the general form for the other two models. Absorb it. Absorb it, quickly absorb it. Before that, let's do one more example. One more example. One more example. All right, give me the answer, guys. Quickly give me the answer. Give me the answer. Get me the answer to this question. Good. All right. All right. Here we go. Great. Good job. This is how it looks, right? So for find the largest three-digit number, already saying largest three-digit, we can find out as much as we know the family of numbers. So because it's a constant remainder, therefore you say that your family of numbers is nothing but LCM of 6, 8, and 9 k times. All right, k is a suitable value because you want the smallest three-digit number, largest three-digit number, or smallest four-digit number. We just have to put some suitable value there, right? Plus constant remainder, right? Now constant remainder, which is nothing but 2. Good. What is the LCM of all these particular fellows? 72. 72k plus 2. 72k plus 2. That's what you are writing. A suitable value of k. All right, now 1. You can of course do a math and you can do that, right? Because the numbers are simpler. You don't really need that. So you will say that 72 into 10 becomes 720. 720. You can go up to 999, right? You can go up to 999. So what is the deficit here? Already if you are going there, you have another deficit of 280. You have another deficit of 7280, but 72 into 4 becomes 288. Right, 288. Therefore, it becomes a 4-digit number. Therefore, you will say that I just have to do 72 into 3. All right, 72 into 3, another 3 more. Therefore, 72 into 3, technically 13 times. 72, the value of k, if you want to write it directly, you would have written it as 13 times. But that's okay. You can break the number. There is no problem. You can break the number. Right, you can break the number and you can do it. You can break the number and you can do it. Right now, therefore, this has become how much? All right, now this has become 216. All right, this is another 216. Therefore, you will say that, okay, this is 936. But there is a plus 2. 936 plus 2, which will become 938, as most of you got this number. Perfect. All right, perfect. All right, now that's answer there. That's answer. I hope all of you got the model 1 right. Model 1 right. So you should be able to identify the model 1 quickly. Yeah, what is the model 2? All right, what is the model 2? Constant negative remainder. All right, constant negative remainder. Let me explain the model here. Listen carefully. All of you listen. All of you listen. First, let me explain the negative remainder concept here. See, guys, all right, there is a number. All right, there is a, all right, now let me take a number. Let me take the number as 13. Let me take the number as 13. 13 when divided by 5. 13 when divided by 5. We all know that the remainder is 3. All right, remainder is 3. What is the negative remainder here? The negative r dash, I will write it. Negative remainder is minus 2. Yeah, how did you get that? How did you get the negative remainder? So I already told you in one of the lectures. Well, at 3, subtract the divisor. If I subtract the divisor, I'll get the negative remainder. Think about it. I have the negative remainder. How do I make it positive? Add the divisor. Negative remainder is minus 2. How do I make it positive? Add the divisor. What is the divisor in your question? 5. Add it. You will get it as 3. That was the remainder here. Right? That is how you convert negative remainder to positive and positive remainder to negative. Right? Okay. Let's come back here. Let's come back here. If the first model fails, try the second model. Try the second model. What is the second model? Now listen to me. When it is divided by D1, remainder is R1. Assume the information is given like this. There is a number. When divided by D1, gives R1 as the remainder. When divided by D2, gives R2 as the remainder. When divided by D3, gives R3 as the remainder. So on. It can be all right. Now 2 numbers or more than 2 numbers. Does not matter how many numbers. All right, R3 as the remainder. So in this case, you will say that, okay, so when, all right, now therefore the family of, but you notice that R1 minus D1, R1 minus D1 is constant remainder, R dash. But you notice this fact, R2 minus D2, negative remainder, that is common, R dash, that is common. Negative remainder is coming out common. Let's say R3 minus D3, that looks common, all right, that looks like R dash. Negative remainder is constant. Then you can say that the family of numbers, all right, in this case, the family of numbers is given by LCM of the divisors, LCM of the divisors, right? LCM of the divisors plus the negative remainder. Add the negative remainder to this, that constant negative remainder. Second model 2 is what? Constant negative remainder, right? Constant negative remainder. Great. Let's take a look at this example. Let's take a look at this example. What did author say? Hey, my divisors, remainders, and negative remainder. Let me write it here. Hey, what is my divisor? First divisor 6, 8, 9. Hey, what are my respective remainders here? Respective remainders are 2, 4, and 5. Hey, what is the negative remainder therefore? Negative remainder is minus 4, that is 2 minus 6. What is the negative remainder? 4 minus 8, which is minus 4. 5 minus 9, alright, which is also minus 4. Is the negative remainder constant? Yes. So I should have written the family of numbers in this case therefore. Family of numbers is nothing but LCM of my divisors, that is 6, 8, and 9. LCM of my divisors 6, 8, and 9 plus of what is that? Minus 4. What is my constant negative remainder? Minus 4. Therefore, you would say that okay, this time k times, of course, right? There is a k times. There's a k times, it's a generic form, therefore k times. Alright, therefore 72 k times minus 4. Alright, that is the family of numbers. From here you can find out whether you want the largest 3-digit number, smallest 3-digit number, all that can be figured out. It is same as the previous alright, earlier number that you get. You have to follow the same steps. Already you end up at 936. Already you end up at 936. Once you are at the 936, this time you do minus 4. 936 minus 4. Therefore, you will say that this time my answer is going to be 932. Alright, 932 would be a suitable answer here. Right, would be a suitable answer. Great. Alright, now here we go. Alright, that's about the LCM model 2. You would have got hang of this LCM model 2. Third model. Let's go to the third model. So now this time what happens is neither the remainders are constant nor the negative remainders are constant. That's a model 3. Model 3 is neither the positive remainders are constant nor the negative remainders are constant. Right? That's a model 3. Let's take this illustration here. Take an illustration here. Divisors and the remainders. You have the divisors, remainders. Let me write the negative remainder also, remainder dash. What is said? When divided by 6, 2 is the remainder. When divided by 8, 5 is the remainder. Hey, what is the negative remainder? Minus 4. Hey, what is the negative remainder? Minus 3. What is that you are trying to say? Neither the positive remainders are matching nor the negative remainders are matching, or neither of them are matching, right? So therefore you will say that okay, therefore it's a model 3. Model 3 is what? Neither the remainders are constant nor the negative remainders are constant. So how do we express this? Now in this case, what you do is, let me give the generic form, friends. Let me give the generic form. Let's start with 2. Let's start with 2. Or we'll talk about the 3. Or what if there are 3 divisors? We'll think about it at a later stage. Let's talk about the stage of 2's to start with. So if there are 2 divisors, divisor 1, divisor 2, divisor 1 leaves remainder R1. Divisor 2 gives me another remainder R2. The owner says you got to first find out what is smallest such number. First you got to find out smallest such number. Smallest such number. Let me call it as X. Let the smallest such number be X. What is the smallest such number? Smallest such number means 2 conditions. What is the first condition? When divided by D1, the remainder is R1. When divided by D2, the remainder is R2. First find out what is the smallest such number. Once you find the smallest such number, then you can write the family of numbers. Then you can write the family of numbers. Family of numbers is nothing but LCM of the divisors. That remains same. LCM of the divisors, k times plus smallest such number. Who found this smallest such number? You found. You got to fight a little bit to find the smallest such number. Okay, let me give a simple algorithm to find the smallest such number. Smallest such number. Let's write it. Yeah, how can the smallest such number X can be written? Let X be the smallest such number. How can be written? It can be written in 2 ways. When divided by X, 2 is the remainder. Well, therefore you can say that okay, this is nothing but 6A plus 2. What is A? What is A? What is A is nothing but the quotient. It can be written as 6A plus 2. A same X can also be written as, from here 8. It can also be written as 8 times of the quotient plus 5. Therefore, you are saying that okay, this can also be written as 8 times of B plus 5. This can also be written as 8 times of B plus 5. It can be written in these 2 ways, 6 times of A plus 2, or it can also be written as 8 times of B plus 5. It can be written in these 2 ways. Now do what? Solve. A and B are integers. What we know here, we know that A and B are integers. That much we know, because the quotients cannot be fractions, they are integers. Can it be 0? 0 is possible, but they are integers. Let's be mindful that, hey, they are going to be integers there, right? They are going to be integers, right? They are going to be integers. Hang on, guys. Change this 5 to hang on. There is an absurdity in the question. There is an absurdity in the question. Let us change it first. Otherwise, we'll not get the answer to this. Right? We will not get the answer to this. There is an absurdity. Now, don't worry what is that absurdity. Let me change this question. right? This 6 you change it to 5. That makes sense. Let me change this to 10. Let me change it to 11. Let's take it as 11. Okay, I removed the absurdity. There was absurdity. Just change this 8 to 11. Change this 8 to 11. Becomes suitable now. Yeah, this is better. All right, 11b plus 5. All right, let's change this. We change it to this. So one way of dealing with this, what you do is, now look at this. All right, take 6a here. 6a is equal to 11b plus 5 minus 2. Take this minus 2 to the other side of the equation. Solve this part. Take it to the other side, 11b. Good. All right, now therefore you say that 6a can also be written as 6a is nothing but 11b plus 3. Now what you do is put some tiny values for this b. Start putting tiny values for this b such that this becomes a multiple of 6. Because your idea is to find the smallest value x. Now don't put any number of your thought. Put the very tiny value, which means what? Start with 0. 0 does not work, put 1. 1 does not work, put 2. 2 does not work, put 3. 3 does not work, put 4. Likewise. All right, likewise I want you to put and check, because now look at the left hand side. Your left hand side is a multiple of 6. Therefore the right hand side should also be a multiple of 6. All right, that also should be a multiple of 6. Therefore put some tiny values. Why? Because you are finding the smallest value of x. Smallest value of x will come only when you take the smallest value of a or smallest value of b. Now what you are trying to do? I am trying to find the smallest value of b. All right, I am trying to find the smallest value of b. All right, let's put the first case here. Let's put the first case and check. Will 0 suffice? Can, if I put a 0, will it be divisible by 6? No. If I put 0, 3 is not divisible. Done. Okay, let's go to the next one. Can I put 1 here? Next test case is 1. Can I put 1 here? Then 11 times of 1 plus 3, 14 is not divisible. Done. Okay, let's go to the next one. 22 plus 3, not divisible. Done. Okay, shall I go to the next one here? 3 works 11 times of 3. 33 plus 3 becomes 36. Therefore, you are now saying that, okay, for a value of b, 3, it works. Good. So you got the value of b here. What is the value of b here? 3. Put that in perspective now. Therefore, you are saying that 11 times of 3 into 5. That is 11 times of 3 into 5, which is 38. Now you are saying that, look, 38 is smallest such number. Smallest such number is 38. What do you mean? 38 when divided by 6, 2 is the remainder. 38 when divided by 11, 5 is the remainder. You got smallest such number. Right? You got smallest such number, which is 38. Now, therefore, how do I write the family of numbers? Therefore, the family of numbers is LCM of. Therefore, the family of numbers is LCM of the divisors, that is 6 and 11. 6 and 11 k times plus smallest such number that you found out, which is nothing but 38 in this case. Therefore, you would say that, hey, it is 66k plus 38. Now, for some suitable value of k, you will get the largest number of 3D, all right, now 3-digit number, etc. All right, that's not a concern. So my point is, all right, now, so how do I get this? All right, what is the methodology on this? The methodology is, all right, now first you find the smallest such number. What is the model 3? First of all, model 3 is neither the positive remainders are constant nor the negative remainders are constant. Neither the positive is constant nor the negative is constant. That's when you say that it's a model 3. How do I write it? Already, what is the algorithm for this? So now you will say that your onus is to find the smallest such number and then plug it into this master. All right, and then plug it into the generic form. Then you got to plug it there. Okay, while finding that, what do we do? So we'll find that, okay, two equations. We'll form all it. Now we'll write the number in two forms. We'll take the smallest number bx and we'll write it in two forms. And then we will solve it. We will solve it very methodically, systematically. We'll solve it. We'll start with putting the value 0, 1, 2 like this. One side we'll have a reference point. What is the reference point? It's a multiple of 6. With that reference point, we're trying to find out, will I be getting a multiple of 6 on the other side? Of course, when we go to algebra, we'll find out advanced ways of dealing with them. Well, that's not the chapter study now. The idea is to understand the LCM model now. How to resolve these equations? Sure, we'll talk more about it as a part of algebra. I will remind you. When I go to algebra, I will remind you, hey, this also we did in the LCM model. Now look at this. We can look at it in a faster perspective like that. Okay, yeah. So that we'll take it in algebra. So this is how it looks. All right, this is how it looks. All right, 0, 1, 2, 3. All right, when you are going systematically, at 3 you are getting a value. Go back, plug this 3. Or you get the value of a, that is also fine. Either a or b is required to find a value of x. One of them is enough. You found that value. Then you wrote the generic form. Based on the generic form, whether you want the largest 3-digit or smallest 3-digit, whatever you want, we can put a suitable value of k and we can solve it. Right, and we can get the answers there. Great, all right, now, so that's about the LCM models. Let's go to the HCF models. There are two models of HCF. Let's get on to the HCF models. Find the largest number which divides this, leaving 6 as remainder in each case. Again, constant remainder. What is the first model? Constant remainder. All right, first model of HCF is constant remainder, leaving the constant remainder in each case. That's a first model of HCF. Just like where the first model of LCM, where the remainders are constant, here also the remainders are constant. Now listen to this, friends, carefully. So therefore, what I should be doing here, first number 126, 123 minus 6, I should do minus 6 here, and I should do minus 6 here. If I do minus 6, my first number will become 123 minus 6, all right, which becomes 117. All right, here it is 130. All right, here it becomes 143. Okay, so I need to find the HCF of these numbers. Fair enough. HCF means what I already taught you. Take the difference. What is the difference? 13. Take the difference. What is the difference? 13. 13. Okay, I got the constant number 13 here. Now I'm checking. Does 13 divide this number? Because if it is not 13, what are the factors of 13? 1. If 13 is not the answer, then 1 is the answer. Fair enough. First, let us check. Will 13 divide this? 13 divides this. Will 13 divide this? Yes. Does 13 divide this? Yes. 13 divides each one of them. Therefore, 13 is the number. The largest number which divides, therefore number is 13. 13 is the number which divides this to leave 6 as the remainder, divides this and leaves 6 as the remainder, divides this and leaves 6 as the remainder. Now listen to me. Therefore, all you got to do is whenever author is asking, find the constant remainder. This is the point I'm trying to make. Right? Divides. Largest divisor you want, you have numbers here. First number leaves the same remainder R. You have the second number leaves the same remainder R. When the third number, there is a divisor. When the divisor divides the first number, leaves the remainder R. Second number leaves the same remainder R. Third number leaves the same remainder R. In that case, what you are supposed to be finding? You are supposed to be finding the HCF of N1 minus R. That's what you did, friends. N1 minus R. All right, N2 minus R. N2 minus R or N3 minus R. Or N3 minus R. This is what I'm supposed to be finding, or this is what I'm supposed to be finding to get the value of D. There is no family of D here, only one D, because there is only one largest number, HCF, right? There is only one largest number. Now don't try to write the families, etc., etc. My point here is, now listen to me carefully. All right, if you are dividing this by cell, if you are subtracting 6, 6, 6, you are anyway taking the difference. Now the difference remains same even before dividing that particular, even before subtracting that number 6. Point is, you have this 123, you have 136, you have 149, you have this there. All right, you have this there. Simply take the difference here, 13. Take the difference here, 13. Okay, now just check for this, because 13 is the number that you got. Thus 13, divide this particular number to leave 6 as the remainder. Check it at that stage, that is also fine. 13, all right, now you divide this. Is the remainder constant, remainder same? Yes, remainder is 6 here. Check this. Does this divide 13 and leave the remainder 6? Yes, it leaves the remainder 6. Likewise, you can do it directly. You don't have to necessarily subtract 6 and do this. Which means, if author says leaves the same remainder instead of this word 6, had the word been same, or that also would have been sufficient, because he don't have to give me this R. He can blank it, and he may say that, okay, remainder is same is enough. Remainder is same is what? This is the approach. All right, this is the approach. All right, N1 minus R, N2 minus R. R may not be known, but does not matter. You can just find the HCF. You can just find the HCF of N1, N2, N3. All right, find that HCF there itself and assume that, okay, after that you will be getting certain remainder when you divide that number. All right, when you divide this by that particular HCF, that you are getting the difference. Basically, find the difference. Basically, what I'm trying to say is find the difference. Find the difference, as you said. Find the difference. All right, till the last moment, till the last point, find the difference. Now take this difference, or take the factor of this particular difference, and divide them and check, are you getting the same remainder. Next example will tell you this story better. Okay, capture this, same remainder. This is what we are technically supposed to be doing. That's one model. Let's take a look at this. It will tell you the story. This will tell you the story. Okay, you saw this. Now he says that same remainder is not given. Author simply said that, man, it leaves the same remainder. But did he say what is that remainder? No. Or did he say what is that remainder? Absolutely not. He didn't say anything about it. All right, now all he's saying is what? Look, all right, when you divide it, all right, by a divisor, certain divisor, it's a 2-digit prime number. That's all he's trying to say, 2-digit prime number, which means because I give very scanty information, you'll get a lot of answers, but pick the answer which is a 2-digit prime number, and it leaves the same remainder in both the case. Fantastic. All right, now what do you do? Take the difference. All right, what do you do? Take the difference, because you are supposed to be finding the HCF after taking the difference. All right, now after taking the same remainder called R. But does not matter, because whenever you are taking the difference remains same. That's what I tried to tell you there. All right, your difference remains same. So therefore, all right, now take the difference on this. Let's take the difference on this. All right, when you take the difference on this, all right, that is 27,584 minus 26,854. Right, now that's the difference you are taking there. Right, so if you take that particular difference, you are getting it as 6, you are getting it as 27, 75, 68, 630. Right, that's a difference is 630. All right, so either 630 is the answer, either 630 is the answer, or the factor of 630 is the answer, or the factor is answer. Now author is very clear, 2-digit prime number should leave the same divisor. All right, now go here, how 630 can be written as 63 into 10, 63 into 10. So what are the prime factors? 63 is a prime number, 5 is a prime number, 2 is a prime number. Which is the 2-digit prime number, therefore which divides 630, because it should divide 630 also before dividing these numbers. 63. All right, therefore 63. Therefore author is saying that, look, take these numbers, divide it by 63, it leaves the same remainder. Therefore you are saying that, okay, the 2-digit prime number which divides is nothing but 63, because 630 can also be the answer. But author said that, look, you get many answers. All right, no, but then I don't want the largest number, I want the 2-digit prime number which does this function. Therefore you are saying that it is 63. What is the model being used in this question? HCF model 1. All right, HCF model 1 is what you went on to use. Okay, let's go to the second model. I guess so far it is good. I guess so far it is going good. Yeah, nice. All right. Okay. Find the greatest number that divides this, leaving different remainders. Now, what is the mod? What is the HCF? Not LCM. HCF. Okay, HCF model 2. Yeah, what is the HCF model 2 trying to say here? The remainders are different. The remainders are different. All right, the remainders are different. Find the greatest number that divides this, leaving the different remainders. Okay, what did we learn in the HCF model 1? Well, HCF model 1 is when the remainders are constant, ignore them, that constant remainder, we ignore them, directly find the HCF of the given numbers. That's what we said. But here we can't do that. All right, here we can't do that. 5, 9, 13. In this model, we have to necessarily subtract a 5, necessarily subtract a 9, and necessarily subtract a 13. Here we have to necessarily subtract that before you find the HCF. In the earlier model, you don't have to necessarily subtract. That is what you saw in the previous example. All right, that's what you saw in the previous example. When he said same remainder here, all right, when he said the word same remainder here, all right, did we bother what is that particular number here? We didn't bother what is that number here, and we got your answer. But here we can't. All right, now here we can't because the remainders are distinct. Here we can't because the remainders are distinct. All right, here the remainders are distinct here. All right, distinct remainders. Therefore, I got to do this first. I got to do this job first. After doing this job, I need to find the HCF. Technically, I have to find the HCF as number 1 minus R1. Number 2 minus R2, number 3 minus R3, number 3 minus R3. This is what I technically be doing to get the greatest divisor, right? Okay, greatest divisor. Let's do this. Let's do this example just to illustrate what is the HCF of the first number here, 115, right? The next number, I'll let know 207. Third number, I'm subtracting here, friends, 312 minus 13, which is 299. Good. Therefore, you are saying that HCF of 115, 207, 299. How do I do that? Get the difference. All right, how do I do that? I'll let now take the difference between them. All right, therefore, this is 92. Take the difference. This is 92. Therefore, you got the difference as 92. Fair enough. Either a 92 should divide these numbers, but 92 is an even number. It does not divide. Okay. If it is not 92 factors, keep writing the factors. 46 is a factor. 23 is a factor. Right now, so you will say that 46 also even number, but these numbers are odd. These numbers are odd, therefore 46 does not work. 92 did not work. 23, will this 23 works? 23 will divide this number? Yes. Does 23 divide this number? Yes. Therefore, you say that 23 is the number. Alright, therefore, you are trying to say that either 92 is the answer or the factor of 92 is the answer. Quickly keep writing the factors. The factors will give you the story. Alright, factors will tell you the story. Okay, by now you must be very comfortable with the LCM and HCF. Now, these are the things you should know about LCM, HCF. I spent good 70-80 minutes on this, because this is a very, very important concept of numbers. One of the very important concept of numbers. Great. All right. Let's go to the next concept now. Let's open up to the next concept called successive division. Let's go to the next concept called successive division, which means what we did, we divided by one. All right, we divided a number by divisors individually. But what if I do it successively? What if I do it successively? Let me take a simple example to illustrate here. Let's read this question. It's pretty simple. Let's read this question. Let's read this question. Only the first portion. Let's read the first portion to understand. A number when successively divided, and note the word, successively divided by 8 and 5. Successively divided by 8 and 5 in that order. All it leaves remainders 3 and 4 respectively. leaves remainder 3 and 4 respectively. What will be the remainder when the same number is divided by 40? We'll come to the second part later. What does the first part mean to us, friends? What does the first part mean to us? Let's understand this now. Listen to me carefully. Listen to me carefully. There is a first divisor. It has led to the first remainder. Now, I took the quotient of this divisor. Then I divided it by T2. That has given me the second remainder. You didn't understand? Okay, let me tell you again. You didn't understand? Let me take simple number here. Let's say that my number is 65. Let's say that my number is 65. Say that number is 65. First, I want to divide this by 3. I want to divide this by 3. Then I want to divide this by 4. I want to understand what are my remainders. Great, let's understand this. Take 65. That's my number. My number is 65. I'll first divide by 3. I get a quotient here. Right? What is my quotient here? 21. All right, which is 63. Therefore, 2 is the remainder. Good. 2 is the remainder. So when divided by 3, the remainder is 21. Now, successive division. When it is successively divided by 3 and 4 means, don't take 65. Take this 21 now. Take this 21. Divide this by 4. That is the meaning here. Take this 21 and divide this by 4. Great. I'll divide this by 4. 4 5 times 20. 4 5 times 20. 1 is the remainder. I will write 1 as the remainder, friends. I will be writing 1 as the remainder. That's the meaning. I took 65. When successively divided by 3 and 4, it left respective remainders of 2 and 1. This is the meaning of this question. Alright, this is the meaning of this particular question. Alright, yeah, that's what I'm trying to say. You don't take this 65 again, which means when you divide by 4, you don't take 65 and start dividing by 4. And you don't take this 65 and divide by 4. What you do is, you take the quotient of the first division. First division quotient was 21. You take that quotient and then you divide. Okay, that is what we mean by the successive division. Okay, let me already now, without wasting much time, let me get onto the point here. How do I do this? Already now, it left something like this. How do I get? Again, I'll get the family of numbers. There is no one single number here, friends. Already infinite series of numbers I will get. I will get the family of numbers. Alright, not just one number. I get the family of such numbers. Let me show it to you. What does it mean? How do I do this? Remember this. Alright, now remember this. Alright, now so how to work on this question? Remember this. When you are alright, now list it like this. First write it like this. You got to first write it like this. Then what you do is, whenever you are coming down, you should add. Whenever, then you should go like this. This is a direction. You have to start here. This is the starting point. Start here. Just remember this algorithm once. It's easier. Start there. Whenever you are coming down, add. Whenever you are going up, again you have to go up to the next divisor, multiply. Whenever you are coming down, add. And then end here. Now end at the last remainder. End. Basically it is zigzag. Listen to me carefully. Come down like this. Up, down, up, down. Now coming down. This is the way. This is the movement. This is the movement. It's the starting point. Here you start. And here you end. Here you end. That is the movement. Just remember this movement. That's easier. Just remember this diagram. Up, down. Now you have to come down first like this. Then you are going up. While you are coming down, it's an addition sign. Whenever you are coming down, addition sign. When you are moving up, it's a multiplication sign. I'll explain this. Don't panic. I'll explain this. Alright. So what are the numbers here? 8. Respective remainder 5. 5 divided by 5. Here guys, 8. Respective remainder 3. Respective remainder 3. Divided by 8, respective remainder 3. Divide by 4, divided by 5, the respective remainder 4. It's a successive division. Right? What happened here is a successive division. Now listen to this algorithm carefully. Whenever you are coming down, it is the plus. Whenever you are coming down, it is the plus. Whenever you are going up, it's into. Alright, now here it is into. Now this is plus. Alright, understand this very carefully. Now can I add 5 plus 4? Yes. Alright, now in the dummy, you can take the dummy here. 5 into 0, you can do first case, 5 into 0 plus 4. Hey, what is 5 into 0? 0. What is 0 plus 4? Alright, now when you come here, it has become 4. Therefore, the result that you are writing is 4. So far, the result is 4. Why? I took first quotient as 0. Just follow me. Don't panic. Hey, why is 0? Don't panic. Hang on. Just follow me. First take 0. Always take 0 first. Take 0 first. 5 into 0. Just do it into here. 5 into 0, 0. 0 plus 4. Alright, 0 plus 4. The result has become 4. Now what you do? Take this result 4. 4 into 8, 32. 4 into 8, 32. Alright, now what did I do? Into, right? This into 4, because the result was 4, 32. Good. 32 plus 32 plus 3. Alright, therefore the final result has become 35. My point is 35 is the smallest such number. 35, what I'm trying to say is, look, 35 is smallest such number. 35 35 when divided by 8, 35 when divided by 8 leaves 3 as the remainder. When it's successively divided by 5, then it leaves 4 as the remainder. 35 is smallest such number. Okay, let me illustrate this. Let us do the division. Let's see. I'll take 8. I'll divide 35. 8 4 times 32. 8 4 times 32. 3 is the remainder. That's 3 I listed here. This is the 3. The 3 has come here. Take this 4. Take this 4. Let's divide this by 5 now, because the next divisor is 5. 5 0 times. All right, now that's a 0 you got here. 5 0 times 0. Therefore, what's the remainder? 4. Perfect. All right, now that's what you got there. All right, that's what you got there. Okay, let me change the matrix. Let me change the matrix. Therefore, 35 is the smallest such number. Keep it in mind, friends. Let's keep that in mind. Let me change the matrix. Let me go to the next one here. Let me change this matrix. Let me go to the next one. Okay, so what if I change this number to 1? Let me change it here. Let me change it here. Next one, next reading if you want. Change it to 1. Change this bracket to 1. Change this bracket to 1. This is a simple truth you should know. This is a simple thing you should know about successive division after the concept is over. Okay, yeah. Alright, I did this 1. I took this as 1. 5 one time, 5 plus 4, 9. Plus 4, 9. 8 into 9, 72. 8 into 9, 72. Because when you go up, it's multiplication. 72. 72 plus 3, 75. 72 plus 3, 75. You are saying that hey, after 35, the next number is 75. After 35, the next number is 75. 75 is the next number. Alright, 75 is going to the next number. How? Let's check this. Alright, now 75. Take 75. Check once. 75 when divided by 8, because the first divisor is 8. First divisor is 8. 75 when divided by 8. I'll 8 9 times. 72. 72. Remainder is 3. Absolutely. That's what we listed here. Alright, that is what we went on to list here. 3. Okay, what I should do with this 9? I should divide this by 5. Alright, therefore you are saying that 5 1 time 5. What is the remainder? 4. Alright, now that is the 4 you listed here. What is this one here? That is the one that you have taken here. Therefore 75 is the next number. So if I change this number to 2 now, if I change this particular number, if I change this to 2, you get next reading. Therefore it's an infinite series. Alright, therefore it's an infinite series. Okay, I hope all of you understood this zigzag matrix here. Zigzag matrix here. Therefore, how do I write the family of numbers? Let me come back and write family of numbers, friends. Therefore, let me come back and write family of numbers. Family of numbers, listen carefully. Therefore, the family of numbers is given by, we understood how to find the smallest number. We understood how to find the smallest number. Let us call the x as the smallest number. That's onus is on you. I taught you how to find. Let x be the smallest number. Let x be the smallest such number. X be the smallest such number. Okay, we understood smallest such number. Now you find that the family of numbers, is nothing but the product of the divisors. No LCM, no HCF. Product of the divisors. In this case, it is 2. What if it is 3? It is 3. Product of the divisors, k times. Product of the divisors, k times, because you keep changing the value. K is equal to 1, 2, 3, 4, etc. You start getting the values there. Product of the divisors plus smallest such number you found out. Who found out this x? You found out this x. Okay, I want you to keep this in mind. This is the algorithm. Alright, this is the algorithm. Okay, let us apply it here. Let's apply it here. Did I find the smallest such number? Yes, 35. We already found the smallest such number, 35. Alright, smallest such number is 35. Fantastic. Alright, we found that smallest such number. Let's do it once again. Whenever you want the smallest such number, I said that start with 0. Whenever you want the smallest such number, I said start with 0. 0 here. 0. 5 0 times 0. 0 plus 4, 4. 8 into 4, 32. 32 plus 3, 35. So therefore, the smallest such number is 35. You stop here. That's the smallest such number, x. You end here, right? Now, this is the starting point. This is the start. And you hit this number, which becomes the end. At the end, what did I get? 35. Smallest such number is 35. Fine. So therefore, you are now finding that what is the family of all such numbers? Family of all such numbers is nothing but the product of the divisors. 8 into 5. How many times? K times. Plus, what is the smallest such number that you found out? 35. 35 is the smallest such number you found out. Good. Therefore, what is the general form, friends? General form for this case is going to be 40k plus 35. Plus 35. Put k is equal to 0. You'll get the first value. Put k is equal to 0. The smallest value becomes 35, because that's what you found out. 35 is already there. Alright, okay. Put k is equal to 1. You'll get the next value of the series. Alright, that is 40 into 1 plus 35. Alright, which is nothing but 75. That's what I showed some time back. Likewise, okay. If I want any nth term here, I can find out. Nth term I can find out. Hey, what is the next term? Put k is equal to 2. 80 plus 35. Alright, which is nothing but 150. Alright, which is nothing but 150, 80 plus 35. Alright, likewise, you can go on to find this here, right? Now you can go on finding it here. It's an infinite series. I hope all of you got hang of this. I'll do one more example. I'll do one more example just to illustrate this point and get a clear hang. Okay, let's go to this question. What's the answer to this question, by the way? What will be the remainder? Question is, what will be the remainder When the same number is divided by 40, good. What is the number here? I have to write this, right? I have to write this. I have to write this. Therefore, family of numbers, you are saying that man, family of numbers is nothing but 40k plus 35. We learned the division algorithm yesterday. Divide by 40. Fine. I'll divide this by 40. I divide by this 40 and remainder. Divide this by 40. We'll get the remainder. Great. 40 by 40, what is the remainder? 0, irrespective of the value of k. 35 by 40, what is the remainder? 35. We learned this. We learned this technique in the numbers lecture 1. Refer to that. Already we learned this. We learned this already. Now we learned the division algorithm there. Okay, 0 plus 35. Final answer is 35. That is the required answer here. In the sense, he was asking that, tell me the smallest such number. Tell me the smallest such number. 35. Good. All right. Let's go to the next one. Next one. Try that algorithm. That crisscross. Try that zigzag fashion. Try that zigzag fashion. All of you try it. Got it? Good. Good. Yeah, here we go. This is what you did. 4, 5, 6 successive division, respective remainders. This left a remainder of 2, remainder 1, remainder 3. Smallest, well, let's find such smallest 4-digit number. Okay, we'll go to the 4-digit number. We know the generic form. The generic form is what? Family of numbers is nothing but product 4 into 5 into 6, not LCM, product k times plus smallest number that I found out. This is the k catch here because this is simple. All right, now this part is simple. This is 120k plus, all right, now this x is the catch here. If I find that x, then my job is done. Then I can find the smallest 4-digit number somewhere closer to 1000, just around 1000 mark, right? So I can find that. That should not be a concern. Fine, let's go here. Let's find this out. Let's find it out. So how do I find the smallest such number? This algorithm. Let's go here. So you put the numbers like this to perspective. We'll continue this. Okay, whenever you're coming down, it is plus. Going up, into. Coming down, plus. Going up, into. Coming down, plus. Let's do that. First number, whenever you're finding the smallest number, what did I tell you? I said that we'll take this as 0. I said that we'll take this as 0. Good. All right, now 6 into 0, 0. 0 plus 3, 3. All right, therefore here the value is nothing but 3. Okay, go up. 3 into 5, 15. 3 into 5, 15. Whenever you're going up, what is the sign here? Into. That's 15. Coming down, plus. 15 plus 1, 16. So here it is 16. 16 into 4, you're going up. 16 into 4, 64. Right, 64. 64 plus 2, 66. 66. Therefore, you are saying that smallest such number is 66. 66 when successively divided by 4, 6 and 5 leaves the respective remainders of 2, 1, 3. Or it leaves the respective remainders of 2, 1, 3. Therefore, 120k plus 66, that's a family of numbers. All right, that's a family of numbers, right? A suitable value. All right, suitable value of k. All right, no suitable value of k. All right, suitable value of k. All right, where we will be hitting somewhere closer to the 1000 mark. All right, 1000. All right, somewhere closer to the 1000 mark is nothing but 13. All right, 120 into 13. Right, sorry. Sorry, all right, 120 into 7. All right, this is 12 into 6. 80, all right, 12 table. Just go with the 12 table. 12 table, go with the 12 table. 12 into 6, 72. 12 into 7, 12 into 7, 84. All right, 12 into 8, 96. Therefore, I can take up to 8 times plus 66. Plus 66, that's the smallest value, right? Now, therefore, you are saying that 960 plus 66. All right, therefore, the smallest such value is nothing but 1026. 1026 is the smallest 4-digit number. The finding here is not a problem. So if you can reach this place, all right, finding that number is not an issue. Finding that number is not an issue. Once you reach this generic form, the job is fairly done. Hey, why these methods are important is, you know that in the CAT-like exam, there are boxes, right? Theta questions. Type in the answer, right? That is non-MCQs. You should know how to get those numbers. As long as the answers are integers, designed for integers, they may ask us to type. Sometimes the decimals also they'll ask us to type. That's a different issue. But integers are most fashionable. Therefore, all it we should know how to get that. We should know how to get that. It is not that every time I work with the answer options. That's not the way to learn the subject. That's not the way to learn the subject. We should be prepared for the theta questions as well. If the choices are there, that's a different issue. The choices are not there yet. How do we do that? All right, that concept has to be clear to each one of us. That concept has to be clear. Great. All right. Now that's about the successive division. Successive division. Next concept. Done, guys. Another 20-30 minutes. Another 20-30 minutes. We are right out there. Two small concepts will do. Factorials, the highest power of a number, or highest power of a number in a given factorial. All right, to find the highest power of a number given fact. Let me illustrate this. Take 10 factorial. If I say that, hey, what is the highest power of 2 which divides this? What is the highest power of 2 which divides this 10 factorial so that the remainder is 0? That's a point. Divides means what? Remainder 0. Well, that's an understanding of division, not leaving any remainder. What's the highest power of 2? Of course, 2 power 1 divides. Common sense, 2 power 1 divides. Does 2 power 2 divide? Of course, it looks like 2 power 2 divides. But what is the highest power of 2, right? Now, what is the highest power of 2? How do I do that? Now, listen to me carefully. So, this algorithm is 10 factorial is nothing but what? 1 into 2 into. Right, this is what you are doing here. All right, now 10 factorial is 1 into 1 up to 10, product of first 10 natural numbers. Product of first 10 natural numbers. This is 10 factorial. So I'm asking that what is the highest power of 2? Naturally, the highest power of 2 comes in every alternate number. Every alternate number will supply a 2. Already even number, every alternate number, which implies I need to look here. First, I need to know where should I look. I need to look here. I need to look here, and I need to look here. Okay, take for example, let me give another example simultaneously here. 10 factorial. All right, what is the highest power of 3? Let's say that what is the highest power of 3? Same thing, same number. So you will be writing it as 1 to 10. That's 10 factorial, right? Remainder should be 0. What is the highest? The point is y. What is the value of y? That's what I'm asking here, right? 4, 5, 6, 7, 8, 9, 10. So where you should be focusing here in this question, every third number, focus on 3. You get a 3 here, you get a 3 here. All right, you get the powers of 3 from there. Highest power of 3 means what? Every third number. Don't try to look at 4 and 5, check that I am finding 3 is there. You will not find, right? Every third number. Similarly, if I say that tell me the power of 5, every fifth number. Power of 5 is every fifth number. Likewise, all right, likewise. Okay, great. All right, now that's what you should be doing here. All right, that's what we would be doing. Okay, fine. How many powers of 2 are here? Let me list it. How many powers of 2 I got? 1. How many powers of 2 I got? 2. How many powers of 2 I got? Only 1 because it's 2 into 3. Hey, how many powers of 2 I got? 3. How many powers of 2 I got? 3. Hey, how many powers of 2 I got? 1. Law of indices, add them. 1, 2, 3, 4, 5, 6, 7, 8. Therefore, you are saying that, man, this is 2 power 8. 2 power 8 completely divides 10 factorial. 2 power 8 is the highest power of 2 which divides 10 factorial. Implies, of course, 2 power 1 divides. 2 power 2 divides. Likewise, up to 2 power 8 divides. 2 power 1 up to 2 power 8 divides this particular number. That's what you are trying to say. The best power of 2 which divides 10 factorial and leaves the remainder 0 is nothing but 2 power 8. Well, that's the best power is 8. Well, therefore 2 power 8. Well, 2 power 8 is the number that you are trying to say, or the best power of 2 is nothing but 8. So, okay, now same algorithm. How do I technically should be writing it? All right, how can I technically quickly write it to the perspective? All right, I can write it like this. Take this 10, friends. There is a 10 factorial, right? Take 10. Take 10. It's a factorial. Don't ignore this. Try me ignore this. All right, take it as 10. Simply successively divide by 2. Successively divide by 2. List only the quotient. 2 5 times. What is this 5? Quotient. Don't list the remainder. Remainder is 0 or 1, does not matter. Okay. Now again divide by 2. Why 2? Because I'm finding the highest power of 2. Because you are finding the highest power of 2, stick to 2. Don't change the 2. Because the idea is to find the highest power of 2. A 2 how many times? 2 times. 2 2 times. Remainder is 1. Listen, remainder is 1. Don't write remainder. I'm not interested in remainder. List only quotient. Alright. Now 2 how many times? 2 1 time. Stop, because now 1 cannot be divided by 2. Stop now. Now do what? Just add up these values. Add 2, 5, 2, 1. Just add this quotient. That's your answer. 5 plus 2 plus 1. Just add these numbers. That's 8. Hey, where is this 5? Now listen carefully here. This 5 is here, friends. This 5 is here. In case you are curious, what is that 5 is here? First row. First row. 5 numbers are divisible by 2. That is the 5 you wrote here. 2 numbers here. All right, now so 2 numbers are divisible by 2 square as well. That's the 2 you wrote here. This is the one that you wrote here. This is the one you wrote here. This is the faster algorithm. Why should I all it know? Because for 10 I can write up to 10 and count. Hey, what if I say 100 factorial? I cannot write till 100 and do this. Rather, I will do this. All right, I would rather do this. This is easier to do. Well, this is easier to. I will just put this to perspective and I'll add my numbers. Okay, let me show one more quickly to you. 3. There is 1 here. So how many 3s are here? 1. Every third number gives you the 3. Pit stops, I know where I should stop. It gives me a 3. What about 9? All right, 9 is 3 square. 3 square. There are 2 3s in this. Therefore, I know this is nothing but 3 power 4. 3 power 4, highest power of 3 which divides 10 factorial is nothing but 4. All right, that's the highest power of 3 is 4. All right, highest power, the y value is nothing but 4 here. So how do I do this quickly out here? Quickly is nothing but take 10 factorial, but ignore this symbol, don't bother. Take 10 as the primary number. Divide by 3, keep dividing by 3. 3 times 9. Now 1 is the remainder, don't bother. Again divide this by 3. All right, 3 one time. Now can I divide 1 by 3? No, it does not make sense. It does not leave any quotient better than other than 0. So therefore stop it. So add these numbers, 3 plus 1, 4. That is what you got. First 3 is here. This is the 3 that you are talking about. That's a 3. This is the one that you are talking about. 3 plus 1, 4. All right, that's a 4 that you wrote here. Right, that is the 4 that you have written here. Okay, I guess it made the point here. You made the point here. How to find the highest power of a number. Now let me take a point here. Hey, what is the highest power of 6 here? What is the highest power of a 6? I will take this 10. Highest power of 6, I'm asking, friends. I'm asking this. 10 factorial. What is the highest power of 6? All right, now see 8. What is the highest power of 6, which divides this 10 factorial? So if you put the same algorithm, 10 factorial, if you put the same algorithm, divide by 6, 6 one time, you will say that the answer is 1. All it wrong. All it answer is 1 is wrong. All it answer cannot be 1. Answer would be little better. Answer would be little better. Let me show it to you. Let me show it to you here. Let me take this value and let me show it to you. All right, now let me take for one of the 6's. One of the 6's. This 6 directly cancels this. Okay, therefore 6 power 1 I got. 1 6 I got. Okay, 1 6 I got. Now let me take another 6, friends. Let me take another 6 here. This 6 can divide this 303 into 2. All right, this 6 can divide this. There is a 3 into 2, which is nothing but 6, which means you got another one. Already you got another one. You got another one. Okay, let me take another 6. Let me take another 6. This 6 can cancel this here. There is a 2 into 2 here, and there is a 3 into 3 here. There is a 3 into 3 here. This 6 can cut off 1 2 with 1 3. All right, because in the 9 there is 3 into 3, just split and write. All right, therefore another 6 is gone. Another 6 is gone. All right, another 6 is gone. Great. What if I take another 6? Oh, this can cut this 2 with this 3. 2 into 3 is 6. 2 into 3 is 6. Therefore, another 6 is gone, which means you already done with 4 counts now. Hey, what if I take another 6 here? If I take another 6, all your 3's are gone. All right, now 6 is made up of what? A 6 is made up of a 2 and a 3. 2 is there. All right, 2 is there. Look at this 8. It is made up of another 2 into 2 into 2. There are 2's. 2's is not a problem, but the 3's are gone because the 3's are here. They are gone. There is a 3 in this number that is gone. There is a 3 in this number which is also gone. Therefore, you will say that the highest power of 6 is nothing but 4. But all right, now when you applied the algorithm like 10 factorial and you directly divided by 6, you got only 1, which is wrong. So remember, this algorithm that we are using, this successive division here, this algorithm is true only for prime power. All right, which means 2 raised to power x. Hey, what is this 2? Prime. Hey, what is this 3? Prime. 3 is prime. But is 6 a prime here? Is 6 a prime here? No, composite. Now don't use this algorithm for prime composite numbers. Use it only for the prime numbers. All right, use it only for the prime numbers. Good. Therefore, how I should be doing for 6? How I should be doing for 6? Now listen. How you should be doing for 6? How you should be doing for 6? First, first what you do is resolve 6 into primes. Resolve that 6 into primes. What is 6 here? Divisor is 6. I'm asking highest power of 6. Okay, what is the highest power of 6? Resolve this 6. 6 is made up of a 2 and a 3. I want 1 2 and 1 3 to make a 6. Find out what is the highest power of 2 which divides 10 factorial, because my question is 10 factorial. Don't find for 6. What is the highest power of 2 which divides 10 factorial? We already know. We already did this problem. 5 plus 2 plus 1. It is there on the board already. It is there. 8. Highest power of 2 is 8. Very good. That is 2 power 8. Yeah, what is the highest power of 3 which divides 10 factorial? It is there on the board here. Already it was there, right? Now it was nothing but 4. I wrote it here. 3 power 4. It is here. 4 is here. We already know that. If it is not known, we may have to find out. Okay, this is 4. Now what I should do? Alright, now I need to marry 1 2 with 1 3. Alright, 1 2 with 1 3. How many 2's I have? 8. How many 3's I have? 4. Which means something like this. How many 2's I have? 8. Alright, likewise, I have 8 2's. Alright, I have 8 2's. How many 3's I have? I have 4 3's. You are marrying it. You are saying that, okay, a 2 and a 3 becomes a 6. 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 You may say that, hey, I am still left with 2's. Fine, but you can't make a 6 because there are no 3's. You can't make a 6 because there are no 3's. Therefore, what you are trying to say here, take the minimum. Take the minimum of 8 and 4. What is the minimum of 8 and 4? 4. That's your answer. Alright, that's, I mean, I showed it here. Why 4 pairs? I showed it here. But you can get the minimum of 8 and 4, which becomes 4 as the answer. Okay, now I showed you how to find the highest power of a number in a given factorial if the number is a prime or composite. Prime is what? Something like 2. Something like 2. Composite what? Something like 6. Alright, something like 6. Okay, I will leave a quick 1 minute. Quick 1 minute. Quick 1 minute here. Right, I want you to do the first 3 questions. I want to do the first 3 questions. I'll leave 2 minutes for you. I will leave 2 minutes for you. 2 minutes for you. Do first 3 questions, friends. Highest power of 2, 3 and 5 in what? In 100 factorial. in 100 factorial? All of you find these numbers. Find these numbers, quickly find these numbers. Good. All right. You might have found them. Great. Yeah. Any doubt? You put it in the chat. You put it in the. You already. You can. Any doubts? You put it on the Telegram groups, guys. You can put it on the Telegram group. Okay. Here we go. Find the highest power of the following numbers in 100 factorial. Right. Following numbers. You would have taken this 100 because the first one is a prime number. 2 is a prime. 3 is a prime. 5 is a prime. Therefore, I asked you to do that first so that the rest of it you can handle along with me, alongside me. You took 100. 100 factorial. Factorial symbol you ignore. Divide by 2 50 times. 25 times. Don't change this 2 because you're finding the highest power of 2. Now don't change that. 2 is static. 2 25 times, 2 12 times, and so on. 2 12 times, 6 times, 3 times, 1 time. All right, that's what you do. Add up these numbers. Add up these stick numbers, which becomes 97. Therefore, 2 raised to power what? 97. What is the highest power of 2 which divides? 97, right? 97 is the answer. Highest power of 2 is 2 raised to power 97, which is the answer, right? Add up these 50, 75, and so on, right? Now, so it becomes 97. Good. So what about, now what about 3? Let's see what is the highest power of 3. Same way, take this 100 factorial. Don't change. Keep this 3 static. Now keep this 3 static. 333 times, 90 times, 99. 311 times. Ignore the remainder. Ignore the remainder. Don't bother about the remainder. 311 times. Then 3 3 times. 3 1 time. Add them up. Add them up, which becomes 48. Therefore, 3 raised to power what? 48. 3 raised to power what? 48. Same way it goes for 5. Same way it goes for 5. 5 in 100 factorial. Therefore, you say that 525 times. Then 5 5 times. 520 times. 520 times. 5 4 times. And we are done. And we are done. 520 times and 4 times. 20 plus 4. Therefore, you would say that there's nothing but 24. All right, there's nothing but 24. Good. All right, now, so therefore, here we go. All right, now, these are the numbers I was expecting in the first three cases. These are the numbers I was expecting. Good. All right, now, this you might have done. Let's go to 48 now. Composite numbers. The next two are composite numbers. Let me take 100 first. Let me take 100 first. Then let me come back to 48. Let me take the 100 first. What is the highest power of 100? All right, 100 means what? First, resolve it into primes. That's what I said. 100 in 100 factorial only. What is the highest power of 100 which divides 100 factorial? Fair enough. Let's try and understand this. 100 is nothing but what? 2 raised to power 2 and 5 raised to power 2. No problem. So how many 2's are there in 100 factorial? We already found out. Number of 2's are 97. Here I am ready. Number of 2's are 97. Yeah, how many 5's are there in 100 factorial? I am ready with that data, 24. I am ready with that data, 24. Now, I don't have to take the minimum here. If I take minimum, just like I taught you in the last question, minimum, then the answer is 24, which is wrong. If I take the minimum here and if I write it as 24, then the answer becomes wrong. All right, that answer would become wrong. Hey, why? What went wrong? What went wrong is, okay, I want pairs of 2's here. I want pairs of 2's. I don't want 1 2 at a time. You said that there are 97 2's here, but I have to take in pairs. I have to take in pairs. Pairs means what? Divide by 2. I have to take this in pairs. I have to take this in pairs. I have to take this in pairs because all at 5's also I wanted it what? In pairs. I want 2 2's at a time, which means what is 100? A 100 is nothing but 2 and a 2 and 5 and a 5. I have to take it as pairs. You have written 97, but then I don't want one at a time. I want two at a time. Therefore, what? Divide by 2. Understand how many pairs are there. You may say that, hey, 97 is not divisible. Take the quotient. Take the quotient. How many pairs, full pairs of possible? Take those many pairs there. Therefore, 97 divided by 2, all right, which becomes 48. You'll say that, okay, there are 48 pairs here. All right, there are going to be 48 pairs here. Great. All right, there are 48 pairs. And then, all right, 24 divided by 2, there are going to be 12 pairs. There are going to be 12 pairs. Now take minimum. At this stage, you take minimum. Now the pairs are ready. What do you all know? You have to marry these pairs. You have to marry these pairs. What is the minimum of this? It's going to be 12. That's your answer. All right, that's your answer. All right, that's going to be your answer. Okay, look at for 48 now. Look for 48. Look for 48. Let's close this 48. Look for this 48. Look for the 48. What is the highest power of 48 in 100 factorial? First, resolve it into primes. Resolve it into primes. What is this 48 first of all? Let us resolve this into primes. What is this 48? 48 is nothing but 2 raised to power 4 into 3 raised to power 1. All right, 2 raised to power 4 and 3 raised to power 1. 2 raised to power 4. Okay, what is the highest power of 2 in 100 factorial? It's again 2 boils down to prime number 2. What is the highest power of 2 in 100 factorial? We are ready. That is 97. Ready with that data. For now we are ready. What if already this was the only question? Then you have to be ready. Already you have to find that 97 first. Okay. What is the highest power of 3? What is the highest power of 3 in 100 factorial? Highest power of 3 in 100 factorial. 48. We are ready with that. For now we are ready. 48. Now don't take the minima here. What you should be doing? You need, all right, now you need by all right, 4 2s at a time. 4 2s at a time. You need 2 into 2 into 2 into 2. 4 2s at a time. Okay. So therefore, how many all right, now how many quadruples? How many quadruples? Which means the units of 4 2s will be possible. How many quadruples will be possible here? 24. 24 quadruples will be possible. Okay. How many pairs will be possible here? How many singles will be? 1 in power 1. Single, one at a time. So how many singles will be possible here? 48. Great, no issues. All right, therefore I will take the minima here, because a quadruple of 2 has to be multiplied with a 3 to generate a 48. Right now, therefore 28, 24 and 48, which results in 24. Which results in 24. That would be the answer. This is 100, this is 24 and this is 12. This is 12. These were the required numbers. I hope the composites you got now. Composites you might have got now. You might have got the composites here by now. Already you might have got the composites. Okay, let's do the reverse of this. Let's do the reverse of this, then we'll close. We'll do the reverse of this, then we'll close. This should have been clear to you. All right, this should have been clear to you. Let us take, okay, now here, there is another point here. Let me make one more point quickly out here. All right, let me make one more point here. 100 factorial ends in how many trailing zeros? Let's say that the question is 100 factorial ends in how many trailing zeros? All right, one of the years, all right, the CAT has asked the question like that. 100 factorial ends in how many trailing zeros? Yeah, what do you mean by trailing zeros? Assume my number is 10, 2, 4, 000. Now, trailing zeros are this, not this, not this. This is not the trailing zero. This is not the trailing zero. Consecutive. Trailing zero. Towards the end, how many trailing zeros are there? Well, the number of trailing zeros are 3. Hey, what do you mean? This number can be written as 1024 into 10 power 3. Well, this number can be written as 1024 into 10 power 3. This is the number of trailing zeros. 10 power 3. 3 is the number of trailing zeros. Therefore, what you should be finding out? Number of trailing zeros means highest power of 10. Number of trailing zeros means highest power of 10. So highest power of 10 means what? Now listen to this guys carefully. Highest power of 10 you should find out. What is the highest power of 10 in 100 factorial? Highest power of 10 means 5 raised to power n into 2 raised to power n. Because 10, what is a 10? A 10 is made up of a 5 and a 2. A 10, all right, no, 10, 5 is made up of a 2, 10 and a, okay, look at 10, don't get confused with the 10. Highest power of 10 is what you need to find out. A 10 is made up of 5 and a 2, a 5 and a 2. Naturally, number of 5s will be smaller in number. Number of 5s will be smaller and number of 2s will be larger. Number of 2s will be larger. Therefore, in the exam, you would have found out only for 5. We know that here. Hey, what is the highest power of 5? 24. What is the highest power of 2? 97. Therefore, you would have written it as 24 as the answer. Number of trailing zeros are 24. Number of trailing zeros are 24, because you will find out how many 5s are there in 100 factorial. You will find out how many 2s are there in 100 factorial, right? In 10 power n, already you had this 10 power n. Alright, nothing but what is the highest power of 10 in 100 factorial? Highest power of 10 in 100 factorial. 10 is nothing but what? A 2 and a 5. 10 is nothing but a 2 and a 5. 10 is nothing but a 2 and a 5. So 5s, how many are there? 24. 2s, how many are there? 97. What is the minimum of these two? 24. What is the minimum of these two? 24. Just remember, if it is a trailing 0, it is nothing but the highest power of 10. Highest power of 10 is nothing but highest power of 5 itself. Highest power of 10 is nothing but highest power of 5 itself. Because number of 2s in a given number would be anyway larger than number of 5s. Right? Let's keep that in mind. Trailing zeros is something that you've got to keep it in mind. Okay, let's do this. Let's do this. Find the smallest value of n. Last point, friends. We are done in under 7 to 8 minutes time. 8 minutes time. We are kind of done. Find the smallest value of n such that n factorial is divisible by smallest value of n factorial is divisible by. Now look at the question. It is divisible by 5 power 24. That's what author is trying to say. It is divisible by 5 power 24. Now you tell me what is the smallest value n can take. Because largest value, there is nothing like that. All right, now so smallest value that n can take. Reverse. I'm asking. Okay, this might sound familiar. 100 was the answer here. 100 was the answer here because all right, I took the first example, pretty familiar to you because the previous slide I had this 100 factorial. 100 factorial, because for 100 factorial you got 24 here. You got 24. All right, now therefore that's a number. But how do I get it? How do I get it? Just now I did it some time back, therefore I know it is closer to 100. Yeah, what if I didn't know about this? How do I get this? Now this is how you get this. Say for example, all right, if you have a prime number, if there is, again, this algorithm works only for the prime number. All right, prime number raised to power k. Prime number raised to power k. All right, prime number raised to power k in n factorial. In n factorial. Right now, what is the highest solid? What is the minimum value of n? Such that a prime number raised to power k divides the n factorial. So idea is to find this n. This n is unknown. P is known. K is known. This n is unknown. There is a simpler. There is a approximation algorithm. What does the approximation say is n. In this case, n is marginally greater than. In this case, n is marginally greater than p minus 1 times of k. Marginally greater than p minus 1 times of k. N will be marginally greater than p minus n times of k. You should remember this. Alright, you should remember this. Okay, let me tell you what does it mean to us. Take this example, 5 raised to power 24, you take this. So I'm asking that in n factorial, n should be marginally greater than 5 minus 1 times of 24. 5 minus 1 times of 24. That is, n should be marginally greater than 96. Point is here is what? N should be greater than 96, but a multiple of 5. You may say, hey, if n should be greater than 96, does it mean 97 factorial? No, because n is 96, which implies what? 96 factorial is not the answer. If 96 is not the answer, 97 is also not the answer, because number of 5s, because you're looking for the 5, number of 5s in 96 factorial is same as number of 5s in 97 factorial. Because by going to 97, you don't get any more 5s extra there. So marginally greater than 96 means what? Now 96 and a multiple of 5. 96 and a multiple of 5. What is the pit stop? 100. If not 100, your answer will be 105. Therefore, what you should do, it's approximation, right? Greater than 96. 100 is also greater than 96. 105 is also greater than 96. All right, most likely the answer will be 100. But at times, the answer can be the next number as well. At times, the number can be next number as well. Therefore, what you should do, you should check back. Hey, what do you mean by check back? Take this 100 factorial, because most likely the first one is the answer. Check it once. Okay, divide by 5. 520 times. 5 4 times. Check it. Did I get this? My 24 back? Was that the number which is required? Yes. Therefore, my answer is 100 factorial. 100 factorial. If not, go to the next one. Go to the next one. You should check. That is 105. And you have check. Here it is fine. Okay, take a look at the next one, guys, just to illustrate this point quickly. All right, now, so like illustrate this point, check quickly. 7 raised to power 20. Is 7 a prime number? Yes. Therefore, what do you do here? You will say that, okay, 7, all right, now you will write this. N should be marginally greater than P minus 1 times of K. P minus 1 times of K. That's what you write. Okay, N should be marginally greater than 7 minus 1 time of 20. Okay, therefore, N should be greater than 120. N should be greater than 120. All right, N should be greater than 120. At the same time, it should be a multiple of 7. It should be a multiple of 7 because I'm looking for the powers of 7. It should be a multiple of 7. What is that number therefore? 126. Your next pit stop is 126. A multiple of 7 greater than 120. All of you know how to get this. It is nothing but 126. Say, what if it is not 126? Try 133. If it is no 126 does not work, try 123. So first let me try this, because in all likelihood that is going to be my answer, right? That's going to be my answer. Therefore, let me take that 126 and let me try it first. Therefore, you are right, dividing this by 7. 7 one time, 7 8 times. 8 times, great. 7 how many times? 2 times, done. Therefore 18 plus 2. Did I get back my 20 here? Yes, I got back my 20. Therefore you are saying that, okay, 126 factorial is the smallest value. 126 factorial is the smallest value. Look at the next one. Composite number, 18 raised to power 18. 18 raised to power 18. How do I do? Again, break it, my friends, break it. 18 raised to power 18. Or it can also first factor this 18. What is this 18? 18 is nothing but 2 power 1 into 3 power 2. Raised to power what? 18. Raised to power what? 18. I didn't do anything. I just already now resolved it to primes. 18, I resolved it into primes. Great. So from here, what do you say here? This is nothing but 2 raised to power 18. 2 raised to power 18 and 3 raised to power 36. 3 raised to power 36. We know the algorithm to find both of them. We know the algorithm to find each one of them. In the sense, what is that? What is the answer for this 2 raised to power 18? We know the algorithm. All right, here friends, n. All right, now n should be greater than 2 minus 1 time of 18. 2 minus 1 time of 18. Okay, 2 minus 1 time of 18, which means n should be greater than 18. 20 can be the number, 20 factorial. Let me write it roughly 20 factorial here. Let me write 20 factorial there. All right, 20 factorial should be fine. We want to check, let us check. 20 factorial, let's divide by 2, 2 10 times, 2 5 times, 2 2 times, 2 2 times, 2 1 time. All right, therefore 10, 15, 17, 18. All right, therefore we got that 18. Great, 20 is the number. All right, now all right. Let's go to the next one. Let's go to the next one. 3 raised to power 36. Find the exact similar fashion. All right, take all right now. So you are writing it as, all right, now you are writing this as, all right, right here. Let me write it here itself. Write it here itself. 3 minus 1 time of 36. All right, which has become 72. All right, so this has become 72. Greater than 72 means what? Take 75. If 75 does not work, take 78. That's the meaning that we are trying to say. Let me take the first one, 75. Let me take 75. Let me go with 3. We go with 3. 325 times. 3 8 times. 3 8 times. 3 2 times. 3 2 times. Okay, we are all right. Therefore, all right, now you are saying that 325 times. 3 8 times. And then you are saying the 3 2 times. How much it has become now? All right, it has become 35. All right, it has become, it has become 35. But what you wanted 36. Therefore 75 is not working. Therefore what I should be taking? 78 factorial. 78 factorial. Now what you should be doing here? Take the maximum of the two, because all it has to accommodate both the powers. It has to accommodate 3 power 36 at the same time 2 power 28. Now earlier reverse, you did the minima. Remember, you did the minima here. So when you are doing the earlier one, what did you do? Minima. All right, you did the minima here. All right, in the earlier one you did minima. This time what you should be doing? You should be doing the maxima, reverse of this, maximum of the given two. Maximum of the given two. What is the maximum of the given two? 78 factorial. That's the answer to this question. Therefore, you will say that 18 raised to power 18 is true in 78 factorial. 78 factorial. Great. All right. So today, all right, that's the I'll end it here. All right. Two important concepts we discussed. One, the LCM, HCF, and the successive divisions. LCM, HCF. We found the models as well. There are 3 models on LCM, HCF. 3 models on LCM, 2 models on HCF. Then we talked about the successive division, how to find the generic form of the numbers. Then we talked about the factorial, highest power of a number in a factorial, right? These were the concepts discussed today. Right, in the next lecture, I'll be discussing about the factorials, the unit digit, and I will be talking about the basics of remainders. Now, these are the things which I'll be discussing in the numbers 3 lecture. So here we go. So now it does not end here where I have ended. Your journey begins. Because you watched me doing it. I gave the concepts to you, but you got to practice to internalize these concepts. Whatever I said, you might have understood. That is called touching the brain. I just touched it. Transformation did not happen, my friends. Transformation happens when you start working. I just touched the surface of it. That's a truth of any learning, right? Just like a swimming pool. Outside the swimming pool, the coach has given the instruction and the coach has demonstrated. You get into the swimming pool, you will not be able to swim immediately the stroke that the coach is trying to say. It won't come immediately. You got to practice that stroke. All right, that's when you master that stroke, right? So therefore, your journey begins now. So take out the modules that you have, take out the books that you have on the numbers. So I clearly said which are the 4 concepts I covered today. Go back and look at the questions on these 4 concepts. The rest of the concepts I will speak in the next lecture. Okay, so quick announcements. Whenever you have the doubts, please ensure that you put it on the Telegram group, because I don't see too many doubts coming from your end. Put it on the Telegram group. Join the Telegram group. You put it on the Telegram group. I will try and address your doubts if there are any. No doubts, fantastic. But if there are doubts, let me address them. Okay, and you have the Endeavor online mock going live tomorrow and day after. So tomorrow and day after, register and take those mocks. It will be on the similar lines, or it will be in the new format. New format of CAT is for 2 hours with 40 minutes per section. You will get the first glimpse or first taste of how the 2 hours mock can look like. Right, here we go. All right, I will see you in the next lecture. Bye till then. Stay blessed. Bye bye.